Welcome to Chapter 7 of the C++ programming language by Bjarne Stroustrup. Chapter 7 is all about pointers, arrays, and references. So from Chapter 6, we introduced both types and declarations, and Chapter 7 focuses more on exploring more of the types. So if you recall the Venn diagram we drew, we talked about the fundamental types, so things like booleans and integers and characters, and I think void as well. Today we're sort of zooming out the scope a little bit to look at pointers, arrays, and references. So, beginning with the introduction, just a sort of almost a quick summary of what we're going to be looking at. Pointers, arrays, and references are all language mechanisms for referring to memory. So each of these, in their own special way, refer to the memory. So we can recall that most objects, right, we defined what an object was, resides in a specific memory address. So as a quick sort of recall, memory we kind of think of as a grid where each cell represents one byte, and each byte has a unique memory address, so like 0, 1, 2, 3, 4, and so on. So objects, things like integers, or our variables, or our classes, our structs, they all reside in particular spots or particular cells in memory, particular bytes. And the object in question can be accessed, so read and looked at, if you know both the address and the type. Okay? The address, of course, is important to be able to locate the object, but type is important because of size. For example, an integer in modern machines is typically 4 bytes, 32 bits. So, for example, if it starts at 5, 6, 7, if it starts at address 8, right? If you have a particular integer and it happens to start at address 8, it will take up not just 8, but 9, 10, and 11 as well. It's going to take all these bytes to store the particular integer, right? So it's good to know the address. We know that it starts at address 8, but we also have to know the type. We have to know that the type is integer to know that it takes up 4 bytes, assuming it's a typical modern machine. But in that sense, if you know both the address and the type of the object you want to look at, then you know exactly which grid cells, which bytes, are being covered by that object, starting from the address and expanding across the size. Last thing, the constructs, which are basically like any C++ concept. So constructs that are used for holding and using addresses explicitly are both pointers and references. So these guys really closely look at and work with memory addresses. So 2 out of the 3. So that's the intro. Just a quick overview of what we'll be looking at. And for more information about types and like the sizes of the different types, you'd want to look at Chapter 6. Okay, so 7.2, we're looking at pointers. So in Chapter 6, from my memory, there's a lot of mention of pointers, but no real definition, and that's because the definition is here. So suppose you have some type. So for some type, capital T, right? That's just a generic type, but it could be integers, characters, some user-defined type that will come up later. So whatever type, T star is the pointer, or I should say is the type, it's a new type, pointer to object of type T. So we'll look at that more in a bit more detail, but the adding the star here, or the asterisk, the light is annoying, that says pointer to object of type T. So the T star basically modifies what the type is. T might be integer, for example. Int star is a new type that we created, which means pointer to an object of type T, as opposed to just integer. So what does a variable of type T star hold? If we think about a regular integer, a variable of type int, so if I said like int x, that stores some integer, right? We can assign a value like 5, and that basically means the x variable is going to hold the integer value 5. But if I was to do int star x, that is x, or maybe y instead, or p, or pointer. If I was to do int star p equals, what should go on the right-hand side? What's a valid thing to assign to p? Well, a variable of type t star, where t again is just a generic type, holds the address, the memory address of an object of type t. So I'll write this in pseudocode for now. But actually, there's an example. Firstly, I'll say that the ampersand, right? So you do like shift 7 normally on a typical keyboard. The ampersand is the traditional address of operator. So what does that mean? If I apply the operator ampersand directly to the left of my x value, like this is basically saying the address of x. So we're taking x, to draw this in a grid. Imagine, we have some bytes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's say 16. Let's say at byte 16, we have our integer x, and integers typically take up 4 bytes, right? So x would the value that x holds would be spanned across all 4 of these guys, right? So that's where the integer that is referred to as x is being stored in memory. So address 16, and of course taking up bytes 17, 18, and 19 as well. Pointer p would hold the value of 16 in this case, because the address of x starts at byte 16. So if p, for example, get a different color. If p, for example, is just randomly stored at 6, the value would be 16. Now, the size of a pointer depends on the type of machine you have. For example, if you've ever heard of a 64-bit machine, that means the size of a pointer actually takes up 64 bits, or 8 bytes. For a typical 32-bit for a 32-bit machine, it would take up 32 bits a pointer, so it's equivalent to 4 bytes. So let's pretend this is a 32-bit machine. That means that value of 16 would actually be stored across all 4 of these bytes in binary. You would actually, there'd be 8 switches here, like that, and the value of 16 would be, you'd flick the appropriate switches to make the binary value 16. But that 16 here refers to the address of x. So if we look at that address 16, we would then find the value that is stored in x. So pointers store the address of a variable rather than the value that is associated with the variable. So yeah, that's the original integer x stored in the memory, and then the pointer p stores the address 16, which tells us where x is located. Okay, so that's how that works. And ampersand is the address of operator. Now, let's say we have that address, right? We have that p value. Is it possible to extract the value of x from p? So without explicitly referring to x, is it possible to extract the value of x? And that's where we get dereferencing. This idea of extracting the value of a variable by using its address, right? So the star operator, the asterisk operator, of course we use the asterisk to declare the pointer, but we can also use the asterisk after the pointer has been declared to dereference the pointer, meaning extracting the value. So ampersand is the dereferencing operator. And how it would look in practice is I could say int y equals star and then p. So what this would do is this would dereference p, giving y the value of 5. So, what would happen here is the compiler would say, okay, what's supposed to happen is you would go to the address stored in p, right? So you go to that memory address, meaning you would find x, and then read the value in that memory address, which would be 5, because x stores the value 5, and then assign that value to y. So that's the point of the star. Okay? Travel to that address stored in p, and find the value stored at that address. Yeah, that's pretty much it. And the reason why we call them pointers, just to give a quick explanation, I guess as a diagram, you can imagine you have in memory the value 5, right? And that's that x, right? And x has a particular memory address. So there's an address for this 5 value. The pointer p is also stored in memory, but the value of p is equal to that address. So the address stored in p, right? That's its p. The address that is stored in p is the same address that that 5 is sort of located in, and so we say that p points to the 5. And in fact, because p is also stored in memory, it itself has a different address, which I'll write in red. Say address 2. So something to bear in mind is p pointers also have addresses because they're also located in memory, so they'll have their own unique address. But their value is also an address that is that holds some particular value. So the value of a pointer is an address that points to another object. Okay, good. So that's sort of declaring pointers using the ampersand operator. Declaring pointers using these asterisks, defining them using the ampersand, and then dereferencing them to access the value. Okay, now, declaring pointers to like the fundamental types, like integer pointers or character pointers, pointers to booleans, like the primitive types that we've seen, is relatively straightforward. You basically take that integer example and apply the type you want. But you can get pointers to arrays and pointers to functions even. So I'll just go through the list of examples given. We've seen the first one, so int star pi, right? That just gives us, we're declaring a pointer that is going to point to an integer, right? So it's a pointer variable that's going to point to an integer. Imagine you saw something like char star star and then ppc. What is that second one? So the first one points to an integer. The second one, what's it going to store? What's the value of ppc? Well, there's 2 stars, so you can imagine that it's a pointer that points to a pointer that points to a char, right? It's a pointer that points to a pointer that points to a char. So I guess the way I would probably describe this is, imagine you have a char with some address, so like lowercase a with some address 1, and then imagine you have some other pointer, we'll call it pc, not ppc, and the value of pc is address 1, which lets us access a. ppc, which again would have its own address, we'll say address 3, would store the value of the pointer, of the address for the pointer that points to a. That's the idea there. So the way I've written it is, it's a pointer to a pointer to a char. So the idea is, when you put double star like that, you're saying, I'm going to point to something that is able to point to the original value. Next we sort of talk about, we sort of introduce arrays a little bit, as in the next on the list. Of course, we'll discuss arrays in more detail, but imagine something like this. For now, think of arrays as just sort of a list of values, a list of the same type of values. So in this case, we're saying we have 15, we have an array pointer. What I should say is from chapter 6, we talked about the declarative operators. So a rule from there is post-fix operators come before prefix operators. So applying that to this, what this is saying is we have an array of size 15 that stores pointers to integers. So in this case, I'll change it to like 3 or 5 just to make my life easier. Imagine you have this sort of list of values in memory. So 2, 3, 4, 5, right? So it's 5 spots for our array. The value in each of these is going to be an address that points to 5 particular locations in memory, each of which should store an integer. Okay, that's what this first one's saying. Because we apply the array operator first, those brackets first, that means this thing that we created here is an array which stores the pointers that point to integers. That's what this is saying. Okay, so that's a bit of an interesting case where like you can have sort of an array of pointers, a list of pointers, and it would look like this. This is what AP would look like. It would be 5 spots where each spot stores an address, and each address refers at each address there is an integer basically. Okay, And we know to interpret it that way because postfix operators, like the brackets there, are applied first before the pointer operator. Now, what if we had something like this? Int star PA 15. Looks very similar, except I've explicitly grouped the prefix operator with the name first before we've done the postfix array operator. This means it's a pointer to an array. Again, I'll make it 5, not 15. To an array of size 5 that consists of integers. So before we had an array where each value was an address, right? It was a pointer. This time, we're going to have, imagine we have an array of size 5. 2, 3, 4, 1, 2, 3, 4, 5, right? So a list. But this time, they all have, each spot has integers, not addresses. Remember, this is in memory as well. So each one of these spots will have an address associated. So it'll be like address 1, address 2, address 3, address 4, and address 5. Bear in mind, just for, that says add 1, add 2, add 3, add 4, add 5, for address 1, address 2, like that. That's what each of those say. But bear in mind that I've written it as if these addresses are consecutive. For integers, for example, these addresses will actually be 4 bytes apart because an integer takes 4 bytes worth of space. So the difference between these two addresses will be 4 bytes. So just bear that in mind. But more significantly in this case, we have this address, so we have this array stored in memory. The pointer, the array pointer, PA, is going to be, some allocated memory that stores address 1. That is, it stores the address of the first element. Where does the first element start in terms of address? At what address does the first element start? That's what PA will store. And it's in this order because of these brackets. We're applying the pointer operator first. So we're saying PA is going to be a pointer that points to an array of size 5, and those 5 spots should store integers. So this refers to the array, but PA itself is a pointer that points to the start of that array, points to the first address used in that array. That's how that's interpreted. Then we have function pointers. Or should I do the other one first? How do the other one first? We'll start with a function that returns a pointer. So we have something like this: f char star. So all this is saying, so the int star f char star, all that's saying is it's a function that takes in a pointer to a char and returns a pointer to an int. That's how you interpret this. So you have a function, right? Remember that these parentheses mean it's a function, right? What you put inside the function, inside the parentheses, tells you what the function takes in as input. So in this case, it's taking in a char star, so it's taking in a pointer to a character, so an address to a character. That's what it takes in. And then the prefix star is applied afterwards. So you know it's a function, and normally for functions we put the return type out the front. So this is saying, function takes in a char star that returns the pointer to an integer. So it's the address, it returns the address of an integer. So if you have an integer like 6 with some address, this function will return the address. Return this address, not the actual 6. That says 6, by the way. So if you had some integer 6, it would return the address. That's how you interpret that one. So again, postfix happens first, so it's a function that takes in a char star, returns a pointer to an integer. Now, that's to be differentiated from this one, and this is what a function pointer is. So you can actually store functions inside of pointers, because functions themselves are actually stored in memory. I don't really know how that works yet, but I will one day figure that out. So how to interpret this, though, is it's a pointer to a function that takes in a char star, a pointer to a char, and returns just an int this time. Okay? So again, because we've explicitly grouped the star and the f together using parentheses, this is saying, okay, we apply the prefix first because we asked it to with the parentheses. So this is saying it's a pointer to a function. We know it's a function because we then have the postfix operator parentheses. So it's a pointer to what is a function, and the rest of it is a function that takes in now we apply the postfix, it's a function that takes in a char star, and then we look at the base type for the return. So it's a pointer that points to a function which takes in a char star and returns an integer. So this one would return the 6 value or the -5 or whatever. If you were to dereference this function pointer fp, you would get a function that takes in the char star and returns an integer. So that's what this is. So we call these function pointers. And I think the main purpose of them is to be able to pass in functions as arguments to other functions. It's quite cool. You can kind of sort of do some cool generalizing things by being able to pass in functionality as arguments. It's okay. I think it's okay if that didn't make sense. I hope. But these are the more complicated sort of points you can kind of get. That first one's kind of that says points to an integer. But int star pi or int star p. Points at pi for points to an integer, not pi like 3.14. But int star pi points to an integer. Char, you can get the double star for pointer to char. Int star ap5 is an array with 5 pointers to integers. Int star pa, that says pa. Oh god, I need to write that up. Int star pa with the brackets means it's a pointer to an array of size 5 that stores integers, and this is a function that takes in char star and returns an int star pointer to integer, and this is a pointer to a function that takes in a char star and returns an integer. So that's to summarize that one. All right, now we get a very special type of where are we going? Half an hour. Wow, I am slow. Maybe I can go faster. Now we get a special type of pointer called void star. We talked about void in chapter 6. Essentially, void star pointers of type void are one of the two sort of major reasons we would use void. So the main point of them, so the purpose, is to store and pass along the address of an object without knowing the object's type. So again, it cannot stress enough that void is not for objects with no type, because every object has a type. That's it, yeah. But sometimes in some code, if you somehow do not know the object, in terms of do not know the type of object, then you can only sort of refer to it using a void pointer. So void star can be read as pointer to an object of unknown type. So pointer to an object of unknown type. So this is how the compiler would essentially translate it, unknown type. So translation, so to speak. Repeat that. And any type of object, any type of typical object we think about, like integers and chars and things like that, any type of object, can be assigned to a variable of type void star, right? So pointed to void type. Any object. However, function pointers cannot be assigned to void star, pointer. Okay. Void stars can be assigned to other void stars. So you can imagine if you already have a void star pointer, you can make that the value that's stored in equal to a new void star pointer that you declare. And void star variables can be compared for equality, so checking if they're equal. In terms of if the address that each void star, two void stars, if they're the same, then you know that it's the same object, so they're equal in that sense. Otherwise, you imagine that they're unequal. However, because you don't know the type, you can't really check for values within the addresses that the void star holds. You can only really just check if those addresses are equal. Now, this is where things get a bit tricky. Void star can be explicitly converted into another type. So the idea of converting a type explicitly is called casting. So this idea is called casting, right? But it can be a little bit awkward or a little bit tricky. I should say that other operations on void star, for example, assigning a void star variable to an int star variable. So not int star to void star, but assigning a void star to an int star, to a new int star variable, can be unsafe. Because we just don't know, because the compiler cannot know, like has no way of knowing what kind of object is being pointed to. So just to give a quick sort of code thing, if you had if you had a function f that takes in a void star pointer and returns integer or something, well, that's not important. But if your first bit of code, I'll call this VP for void pointer, right? That's what it takes in. If my first bit of code is int star pi for pointer to integer is equal to VP, right? So I'm trying to take the address at VP and give it to the integer pi, the integer pointer pi. That's going to be problematic because all we know about VP is it stores an address to some object. What is the address of that object? We don't know. So trying to give it to pi, which is supposed to sort of guarantee that it points to an integer specifically, is problematic, right? Because we're going from something that's very general to something that's very specific. So this is unsafe. And just to clarify, going the other way is perfectly fine. And that's what we said. I don't know if I said it here. Maybe I rubbed it out. The thing that said any object can be assigned to, right before this point, any object can be assigned to void star. So if I were to write, if instead of this was int star pi, so if we're taking in a pointer to an integer, and we know that, then we can write void star VP is equal to pi, and that's no problem. This is safe. But if we were to use VP instead of pi in the future, we wouldn't know that it's points to an integer. So this is safe in the sense that C++ knows what to do here. But if we were to use VP in the future instead of pi, then we wouldn't be able to use any type information because VP as type void star has no way of knowing what the type of object is being pointed to. So yeah, other operations, like if you try other operations, such as, what did I say? Like the first thing I said, yeah, assigning a VP to pi. Operations like that would cause compilation errors. And if we want to cast, if you want to use the value or use the object that a void star points to, we have to do the explicit cast. I'll get rid of this now. I'll keep the other line. If you want to use, to use void star, or I should say, to use the object I don't think it's been picked up. There's like loud-ish music being played. That's kind of crazy. It just came out of nowhere. To use the object that void star is pointing to, an explicit cast must be used. So it's kind of on the coder, the programmer, to know what the type should be if you're going to do an explicit cast. So for example, if you were to try to do int star p, and this is the same kind of example where a function that takes in a void star pointer, right? If I was to just say VP, like I said before, that's going to be problematic, right? Where VP is a void pointer. But if we wanted to do that, assignment, we'd have to write specifically static cast, change it from void p to void star to int star, and take in the actual pointer, which was VP. Okay, so what is it saying? It's saying take in VP. You think of this as a function that takes in VP and will convert it into an int star. And only after you do this explicit cast will this assignment to int star p be okay. All right, but if it's not an integer, if VP is not pointing to an integer, then the casting will be attempted, but I'm actually not sure what will happen. It might be undefined behavior, but you wouldn't really expect good things to happen if it's a char instead of an integer and you've casted to an integer. But I'll try that. I'll put some code up. All right. Generally speaking, I will just mention, I think this was said in the book as well, void star is used in very low-level code. It would be very unlikely that the typical developer was to use void star. You'd have to be doing some really, I suppose, generic things that you wouldn't really expect to see at levels any higher than super low-level program. But I'll just read this out. In general, it is not safe to use a pointer that has been cast converted to a type that differs from the type that the object is pointed to. So yeah, so it's unsafe. Again, doing that cast, I think it will work, but it's unsafe if, for example, the void star is pointing to a character and you cast it into an integer pointer. Okay, so the primary use of void star is passing parameters to functions where the function can make no assumptions about the object's type. So again, you have some function f, maybe it returns an integer or something. You take in a void star VP, and the only reason you do that is because the function is not meant to know anything about the object that VP points to. But beyond that, I don't really know. I don't think I've ever used a void star before, because I don't know. Granted, I've been programming particularly long, but I can't imagine when. I have no real example of when you would actually use one. The other purpose would be returning untyped objects from functions. So again, instead of, if you have some function f, let's say this time you take in an integer into x, the return type you could make void star, meaning an address to an object where we don't know the type of the object. Oops, sorry. We can make that the return type, and so all this code will happen, and what will it return? It will return an object. Sorry, it will return the address of an object, but the caller of the function will have no way of knowing what the type of that object is, because it returned void star. Okay, very nice. From there, we talk about null pointer, and I believe null pointer was mentioned a couple of times in passing in chapter 6, but now we can really explore what it is. 7.2.2. I feel like null pointer is relatively sort of transferable across different languages. You'll see things like null. I think in C has null. Maybe JavaScript has all sorts of weird things. I know in Python there's none, which is like the same kind of thing. This idea of a value that is not really a value, like it's about providing a value to nothing, essentially, to the abyss. So null pointer is actually literal. So it's a literal that represents something called the null pointer. So whenever you think of null, nullptr, like that, nullptr, whenever you see that, it's actually the same thing as the null pointer, like that. So the null pointer is a pointer that points to no object. And I don't mean, when I say no object, I don't mean it's pointing to some void object or something. I mean, it literally has no object associated with it. There's no address. I believe it points to the address 0, but the address 0 is never used, basically. It's intentionally left empty, address 0, so that null can point to it, and if you ever try to access the stuff in 0, it'll always come up with an error. And the null pointer can also be assigned. So can be assigned to any pointer type. So you might have int star pi equals null or null pointer, right? So that's some example code. And what is it saying? It's saying give the null pointer to int star pi. That is, make int star pi also point to that 0 address, to that nothing address. And I guess the main purpose of null pointer, in my mind, is like when you need some kind of way of representing nothingness. So the only thing I can think of is linked lists, but I don't know if that's too much to assume. Yeah, imagine you have like some need for an absence of a value. Like you want to give everyone an age. You have some people, you want to give them an age, but some people you don't know their ages. I don't know why, but let's just say. So you might have a list, like an array. I'm not talking about linked list actually. I think I can do this without it. And you have an array, so this might point to some number 5. This might point to number 4. I don't know why everyone's really young actually. This guy's 32. And then the fourth person comes in and you don't know their age. They don't know their age, their birth certificate burned in a fire or something. So rather than giving them sort of a value, you can make them point. You can make the pointer null. You can make this the null pointer. So this is like some address, this is some address, this is some address. All these 3 point to some particular address that gives you a particular number. The null pointer will point to this empty address 0. Sorry, I shouldn't say empty address. It's the 0 address, but in the 0 address there is nothing. There is this concept of nothingness, which means you cannot work with the null pointer. There's nothing to dereference. You try to dereference a null pointer, it blows up. I don't know exactly what it says, but I believe it's a dereferencing error, like a compilation error that says you tried to dereference a null pointer, shame on you, kind of thing. So yeah, that's the general purpose of the null pointer. But the last thing I should mention, I forgot to say. So it can be assigned to any pointer type, like integer pointers or character pointers or whatever. But it cannot be assigned to non-pointer types. Okay, because it is a null pointer. It needs to be given to something that is a pointer. So if you try something like int x equals null pointer, right, that's going to cause errors. Because int x is not a pointer, it is just an integer. So this is fine, this is safe, this is defined, this bad. I believe it will just be a compilation error. I don't think there'll be anything that crazy that happens, but you don't want to give null pointer to things that aren't pointers. Okay, and that's the end of pointers. So hopefully that made sense. So the main takeaways are you have ways of storing the address of things, and using the pointer declaration and using the ampersand operator, and you have the dereferencing operator, which lets you access values via a pointer rather than via the original variable like x or whatever. You can use the pointer to x and dereference it to get x's value. Just gonna close my microphone. All right. Next up, I assume we gone for like an hour. Oh, not even. Okay. 7.3. Arrays. So we've kind of done the first bit, right? That's kind of ticked off. Now we have arrays. So I've kind of been talking about arrays as lists for now because that's like a nice way of just simplifying things. But I did say at the very start that all 3 of these topics, pointers, arrays, and references, are all ways of referring to memory. But if an array is just a list, then it might be unclear how arrays point to memory, or refer to memory, sorry. So hopefully that'll be more clear soon. But for now, we'll just introduce them. So what is an array? So for some type t, so once again, just some generic type, could be ints, could be chars, whatever we've been working on so far. If we see something like t size, it is the type array containing size, we're going to use n, where n is some integer, n is some positive integer, containing n elements, each element with type t. So we've seen a few examples of this previously. We've seen examples of this across the 2 videos so far, but if we see something like a, int a, and then 3 like this, the t in this example is the int, and we have a, and then we have this 3, which is like this part. So this is like the n part in the brackets. So this is saying a, the variable a, refers to an array that contains 3 elements, each of which have type integer. So again, think of an array as a list. In this case, we have 3 spots to store integers, -6. Okay, remember integers can be signed and unsigned, so negatives are fine. But that is the main idea. So still thinking of them as lists is completely fine. Something that all programmers should get comfortable with quite quickly is arrays are 0 indexed. So this idea of an index and position are basically synonymous for arrays. So you look at the first position of an array, you might consider that position 1, but generally speaking in programming, we consider that position 0. And then the second element has position 1, or index 1, and then the -6 would have position 2. So there's 0, 1, 2, as opposed to 1, 2, 3. So in that case, in that sense, we call arrays 0 index because they start from 0. And then after we've declared our variable, we can use the bracket, square bracket notation, square bracket operator, to access an element in an array. So this is the subscript operator, which lets us access the element at position or index I. So index I. So in this case, if we declared A, right, and we initialized it to be 3, 2, and -6, then if we were to then somehow maybe print A of 1, right, we would look at index 1, and this would print 2. Okay, so A of 1 would be is equal to 2. All right. Now imagine we try to access an index that is not valid. Okay, so for example, accessing like 3, for example, or -1. So access, we call this out of bounds. Accessing out of bounds index. This is undefined behavior. So what would happen in this case is not something that's documented. It's not something that the standard expects a compiler or an implementation to be able to handle very well. So this is undefined behavior, so you never want to be doing this. You never want to be accidentally, you don't want to be accidentally accessing indices outside of your range. Which is why knowing the size of your array and making sure you never accidentally try to access a negative index is very important. A couple of other rules in terms of declaration. Variable sizes for an array is illegal. I was surprised by this actually, because even something simple like, imagine you have int x equals 3. That's not very good. Int x equals 3, and then you try to do the exact same line as before, int array, but instead of writing 3 literally, you put the value x. This actually causes a compilation error. This causes an error because essentially we never want to put a variable in here. Now, I believe we talk about const later. I think it comes up in a second, hopefully. Or I maybe talked about it before, I can't really remember. But I think we talk about the const keyword. If we had put the const keyword in front, like that, then this would actually be okay. Because the compiler is satisfied that x is never going to change. Const means it's short for constant, and if you put const in front of this declaration here, x is never going to change. It's never going to be allowed to change. So then this will be fine. But without that const keyword, where x is just a pure variable where it can be changed, its value can be changed, this will be problematic. That's one rule. And if you do want variable sizes or the ability to resize, so for variable sizes, you would use vectors. I think I might have mentioned vectors in passing, but it's part of the standard library, and they're very cool. But it's chapter 31 apparently, so it might be a while till we get there. So what are the purpose? What are arrays, kind of simple arrays, good for? Generally, we're good for simple, fixed length sequences of, I'll say, homogeneous objects. I don't know how often we use the word homogeneous to describe objects, but I just mean objects of the same type. So homogeneous. So it's, that literally as we described it, it's you've got fixed length and you've got the same type of object everywhere. They can be arrays can be allocated on the stack statically and on the free store. Now, these, I believe, we talked about static objects in chapter 6. I need to write bigger. Allocated on the stack statically, those are two different things. Either you can do it on the stack, or you can do it statically, or you can do it on the free store. Static objects, I believe we talked about in terms of lifetime. They once they're produced, they exist and stay alive until the end of the program. That's what that means. And then stack versus free store. I believe free store and heap are synonymous. I have to double check that. But essentially, these are two different types of memory where you can allocate things. Stack. If you allocate something on the stack, though, generally it gets destroyed for you. Like the memory is cleaned up for you. That's like the general thing. And then free store, you are a bit more responsible for making sure that anything on the free store is cleaned up a bit more manually. If you've worked with C before, that might be a bit more familiar. I might look into these two things a bit more. But for now, just think of it as arrays can be put in either one of these two places in memory, and you can also do it statically if you'd like. Yeah, so if you were to write something like int a2 or array 1 10. I'm writing this as a global variable, right? Not inside any function. This would be static. So this is 10 ints in static storage. Static storage just being the place where anything with a complete lifetime of the entire program. Static storage meaning static storage is where any object that's going to last the entire lifetime of the program is stored. It's like a special place. So because this is a global variable, I put it outside any function. It would be put in static storage because global variables are a type of static object without having to explicitly call them static. If you then have a function and then say int a210, this would be on the stack, right? So this is kind of what we saw before, and it looks very similar to this. The only difference is this is a global thing, so it's static, and this is inside a function. It's in the function scope, so it would be put on the stack. Stack is something that can be destroyed. Sorry, things on the stack can be destroyed when the function finishes. And finally, if you use the new keyword, I don't think we've talked much about the new keyword. So you got int star p for pointer. Notice I'm using pointers this time, and then we can say new int 10, right? So this would make an array on the heap, and it's important to notice that when you use the new keyword, you expect essentially to, in essence, get a pointer, get an address of the array. So we assign this to a pointer of int star because that address is going to point to an integer, and the next 10 integer spots are also going to be allocated to this array. So the pointer here points to the first element on the heap for this array. So that's on the free store. Sorry, not on the stack. So those are three different ways you can kind of sort of manipulate where the array is stored. Now, general advice from the book is not really it's in kind of I guess normal programming when you're not sort of doing it as an academic exercise. It's best to use higher level data structures. Best to use higher level data structures. So things like vectors. So there's the vector standard library. There's vectors in the standard library. There's also a library called arrays, or array, sorry, not plural. We talk about arrays in general. There's actually a library called array, and they just have certain properties that make things a bit safer in the sense that you don't have to do so much work yourself. It kind of helps you out a bit more. Again, looking at the standard library is a separate section, so I don't talk about it too much here, but these are helpful, and investigating them is a good idea. Now, it is good to avoid lower level arrays, or simple arrays, like the arrays we've been talking about, not the library array. It's avoid lower level arrays in interfaces, so things like function arguments. Interfaces in general, I believe, means anywhere where you kind of parameterize, like you have a sense of, I'm taking in some input, I'm going to use that input, so like an interface is like that. So function arguments is an example. This is a problem because there is an implicit conversion to a pointer of the first element. So we talked about when we're doing that free store allocation, or that heap allocation, with the new keyword, it actually returns the pointer to the first element. When you pass an array, a simple array, through a function, the actual data that gets passed to the function is a pointer to that first element, not the entire array in that sense. And the book basically claims that this implicit conversion, potentially without the programmer's knowledge, can cause some sort of interesting behavior that you might not expect, and you might have to sort of figure out on your own. if you're going to allocate on the free store, like we saw before on the free store, if you're going to use that allocation, if you're going to make that allocation with the new keyword, you have to you must use the delete with an array, with this kind of array symbol next to it after the final use. This is what I meant by cleaning up your memory. If you put stuff on the free store, it's on you to make sure that memory gets cleaned up. And in this case, using this particular keyword, delete with the array brackets, is how you clean up that memory. Okay, cool. So that's basically introducing the arrays, but we continue on with arrays, looking at initializers. So ways to actually give values to the slots that are within an array, to the spots in an array. So 7.3.1. Array initializers. So I think we've seen before that you can initialize using a list or sequence of values wrapped in the squiggly brackets. So for example, int v1 equals 1, 2, 3, and 4. Now, something to notice in this particular example, something to notice is I didn't actually put a value for the n in here, right? When I declared. Normally when you declare, you put a value here, like 6 or 12. If you were to do this, the compiler is basically able to determine that the appropriate value here should be 4. This is the compiler figuring this out, based on your initialization. Because you gave 4 elements in your initialization, if you do not provide an explicit size, the compiler will figure out the size and will work with that. Yeah, so that's what I won't bother writing that. But essentially, the compiler, this is the compiler's interpretation for v1's size based on the initialization value. Now, if a size is provided, if you do provide a size, providing too many elements in your initialization list causes an error. So if you were to go, int v1 and then say 3 equals 1, 2, 3, 4, the compiler gets confused because it's saying, well, you asked for 3 spots for my v1, or maybe I should say v2. You asked for 3 spots for your v2. You asked for 3 integer spots, but now you give me 4 integers to work with. So how am I supposed to fit 4 integers into 3 spots? So this causes error. However, the opposite, or the other way is the other way. Doing the other way is actually okay. I don't know why I struggle to speak there. If the initializer provides too few elements, so that is the size you give here is bigger than the list, then the unused spots, so the unused spots, so to speak, are 0. So for example, if you said int v3 is 5, but then you only give 4 elements, 1, 2, 3, 4, the array, doing this is equivalent to giving v3 the array 1, 2, 3, 4, 0. This array is essentially identical to this array in this context because the size is 5, so this must have a value of 5. So the last element, because it's unused, because 1, 2, 3, 4, the first 4 spots are used, but the 5th one isn't, that last element is 0. And in the context of integers, it's easy. You just put a literal 0 there. For characters, you would put the you wouldn't put the character 0, but you would put the character that has a value of 0 in ASCII. Right? I believe it's called the null character. I think that's what it is. Yeah. So you put the null character instead of an actual 0. For pointers, you put the null pointer. For booleans, I think you would put false. I assume because again, false sort of converts to 0. If you remember that mapping in the boolean section. What other types are there? Nulls. Float would be 0.0, I believe, like that. So especially most primitive types that we talked, just about every primitive type we talked about has a 0 that would be used in this context. Now we'll get interesting. Okay. This bit's about arrays. Sorry. This part is about memory with arrays. Obviously, it's about arrays. Just a bit of background. Let's say we had code that looks like this: int x equals 3, int y equals x. To talk about what happens in memory, firstly, remember that integers are 4 bytes typically, 32 bits, so 4 bytes. You have your grid, and we have our addresses. I won't bother. But when we do this first thing, 4 bytes are used. 1, 2, 3, 4. 4 bytes. Is the black starting to fade? Okay, I'll change it. 4 bytes are used to store the value 3. In this case, 3 is a very small number, so you wouldn't really need the 4 bytes. But always 4 bytes are going to be used, and this is for the x value. Right? When we see y equals x, what happens is the value in x is copied into new memory for the y. So, in this, for example, you might pick this sort of grid here for the y. Right? I believe memory is just randomly picked. Like the starting address of y is just randomly chosen. But you pick 4 bytes and you store 3, and the way we sort of get the 3, because we didn't ask for y to equal 3 exactly, we asked y to equal x. So in actuality, what happens is there's a copy operation which copies the 3 from here to here. So there's a copy operation. In essence, when you use equal signs between 2 variables, like int y equals this variable x, usually what you expect is a copy operation from the x value into the y memory. Right? So equal signs, assignment operations are usually copy operations in this context. However, there is no built-in copy operation for arrays. And this surprised me. There is no built-in copy operation for arrays. And I really did not expect this because I believe, I guess in Python, it's okay to sort of make one list equal another list in this way. But if you tried something, I think I have code for this. I'll also just put on the board just in case I don't. I can just write something up. But if you were to try int x3 equals 1, 2, 3, that's nice and fine. But then if you were to try int y3 equals x, what I expected was there'd be a copy operation that would allow the 1, 2, and 3 in memory to be copied, all 3 elements to be copied to y's memory in a similar way, except for 3 integers, right? 3 contiguous integers instead of the 1. But this actually results in an error because there is no built-in copy operation. So that was quite interesting. So that's something to bear in mind. Trying to make one array, one newly declared array variable, equal another one in this fashion results in an error. So you cannot initialize one array with another array, and you cannot do array assignment. So this kind of thing is illegal. Okay, something else to mention, and I believe we'll talk about this a bit more. But I'll mention in passing, and then hopefully make more sense in a second. You cannot pass arrays by value. So we talked about that implicit conversion from array to pointer. Trying to pass the entire array into a function, for example, is not going to happen. And we talk about this more in 7.4, so in the next bit. This is 7.3 now. But you cannot pass arrays by value. And if you do need to do an assignment to a collection of objects, so if you need to do an assignment on a collection of objects, like a list or whatever, then once again, we want to use vector library, the array library, or the val array. I haven't really worked with the val array library at all, so I don't really know what that's about, other than maybe it's I shouldn't guess. These are basically 3 libraries that you can use for this kind of purpose of because I believe these all have the copy operator defined in them. But again, array is not these arrays. Array is a separate library that works with arrays, works with simple arrays, but has extra functionality that makes our lives a bit easier. So if you do need to do array assignment, you want to use one of these libraries. Vector, array, and val array. All right. Oh, damn. I thought we were done with 7.3. We are not. We now have string literals. I forgot about. So we talked about character literals and other literals as well, where we write the literal value that we want in code. 7.3.2 string literals. So a string literal is a character sequence, so one character after the other, enclosed. That's not how you spell that. closed in double quotes. So we think about character literals as one character, usually just about one character enclosed in single quotes. String literals, string meaning basically a list of characters, is a character sequence enclosed in double quotes. So you think of something like, think of the classic hello world, right? With the space in between, you've got a list of characters and then enclosed in double quotes, right? Now, a detail that people who do C or maybe work with a bit of C++ will know is string literals are terminated with the null character. I don't know if that's true for all characters, if that's true for most programming languages, but the null character, if you look at ASCII, I believe it's the 0th. It's like the very first thing you see. It's like it's given a value of 0, and I assume they just say NUL or NULL, but in code, we would normally write, if we wanted to get the null character, we would do \0 and then close it in single quotes. That's the null character, and that is what every string is terminated with, like ends with, regardless of sort of what you write. So what I mean by that, imagine, well, if you were to ask the size of hello world, the string hello world, if you were to literally write this, remember that each character, especially ASCII characters, have 1 byte, right? So you might think, okay, well, there's 1, 2, 3, 4, 5, right, for the hello, 6, 7, 8, 9, 10 for the world, and there's also, we can't forget, there's also a space, right? The space, so that's 11, the space is character. So 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, 11. But in reality, there are 12, because even though we wrote 11 characters, every string is terminated by the null character. So when we write hello world like this, what the compiler and the program use is actually hello world with the null character, right? The null character is just a really super helpful way for programs and our computers to know when a string ends, because strings can be very variable in length. So the null character is just a really surefire way of knowing exactly when the character ends. Okay, so what is the type? What is the default type of a string literal? Right, we talked about the default type for a character literal is char, an int literal is integer, a floating point numbers literal is the default type is double. So the type here is const char n, where n is the size of the string literal, again including that null character. So again, we see that const. We see that word const again. Hopefully the char array makes sense. We say char n because it's you can think of it as an array because it is an array. It's a sequence of the same element, same type of element, I should say. It's a sequence of the same type of element, and there's n of them. So char n is an array of chars. The const is basically because string literals are immutable. Trying to change a string literal is going to cause problems in this language. So it's a type const, immutable, can't change it. Once it's done, it's done. And then character array of size n. So that's the type, that's default type. And then assigning a string literal to a non-const char. So assigning to a non-const variable, specifically pointer, generally a char star, is dangerous. Because, so I'll just write it. So imagine you have something like char star p is equal to hello world. Right? On the surface, this doesn't look super problematic. What would happen is this would get loaded into memory, right? You would get the first character's address, and then you would give that address to p, and it would store that value. That's fine, but this gives this kind of implication without the const there. This kind of gives the implication that the value hello world could be changed, right? But in reality, hello world is not going to want to be changed. Hello world, I believe, is written into something called read-only memory. I don't actually know how that works exactly, but it's memory that programs are not allowed to sort of change once a value is written in, sort of thing. So essentially, you're going to try to access an address that's read-only, and then if you try to make modifications, do write operations to it, then it's going to cause problems. I will probably write a program for that to see what happens. But the reason why we say this is dangerous is because this expression here gives the impression that the string is mutable or changeable when it is not, because because this thing here is of type const. If you want to, that's okay. This is interesting. If you want to, should I erase? Yeah. Let's say you want a string you can make mutable, a string that you can change. What you have to do here is do char p and then array operation, yeah, equals hello world. Right. So what does this do? Oops. What does this do? This gives us a mutable string to work with. What's happening in memory? You have this potentially in read-only memory, but this actually gets copied because string literals, I believe, do have a kind of copy operation associated with them. This gets copied into a modifiable array on the stack. So, if this is your read-only memory, this is read-only. You have hello world sort of written in with the \0 in there, with the null terminator, so hello world null terminator. You also have your regular stack memory, where sort of your local variable, or your function variables and your regular local variables are stored. When you do this, this guy gets copied as a copy operation. Done here, so hello world is here, the \0, and p, the array p, gets linked up over here. And this is perfectly okay to access and modify, which is why that's now a mutable string, because this is an extra step of a copy operation when you use the kind of stack memory by declaring like this. So that's the difference between trying to use a pointer, because the pointer will just try to access this memory directly, because it's going to take the address in here. Doing it this way moves it to the stack, which is okay. String literals are statically allocated. So string literals are statically allocated. So what does that mean again? That means that the lifetime of the string literal, is always going to be available. It's always going to be alive throughout the entire program. So why is that helpful? I believe, essentially, yeah, if you had hello world, imagine you wanted to print hello world 10 times, or you wanted to use it 10 times in some way. Because hello world is immutable, you know that's never going to change, so you're pretty comfortable with using it over and over again, because it's in read-only memory. So because it's available throughout the entire lifetime of the program, because it's statically allocated, you can just use it over and over again. If you want to assign a variable to it, and then assign another variable to it, you can always just continuously just use the same one, basically, in memory. So that's why static allocation there is good. It also can, the consequence of this also is you can safely return string literals from functions. Because sometimes you might, so imagine if some function f that returns a string. So you say returns hello world. Because this is in memory, that will persist after the function has finished and the scope of the function is gone. If you have a caller, like in the main function, into main, that then calls f and captures the result equals f, right? There's no extra kind of operations to make sure that the string hello world is safe. The same address or the same hello world that was returned from here is going to be the same hello world that gets assigned to result here. So that's kind of that's nice about that. The empty string, just for details, the empty string looks like this under the hood, right? We would write it as just two double quotes with nothing in them, right? If you were to write it in code, that's what it would look like, but in reality, it has a size of 1 because of the null terminator. In terms of sort of readability, you can break long strings down. Can be broken into multiple lines of code. This is more about like formatting rather than actual C++ implementation, but imagine you have something like char alpha star equals, you can go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Notice though that I put this on multiple lines, and each individual line, like there and there, has separate quotes. So it's as if we had one line A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Like it's the same thing, except we just have to put two sets of quotes, one up here and one down here, in order for this to work. Okay. Raw character strings. I forgot about that. How are we going for time? Okay. Raw character strings. So this is sort of continuing on from string literals. So 7.3.2.1 raw character strings. I believe this mainly talks about regex. So I wouldn't be too surprised if this is only really for sort of a subset of people who kind of are comfortable with what regex is already. In essence, regex is a way of describing sets of strings using a single sort of pattern string. But what that means, that might not mean anything. So this is a very niche sort of topic within string literals, and not necessarily the most helpful information for everyone. So skipping this section won't be the worst thing in the world. With regular, non-raw string literals, we may want a quotation mark, double quote, or a backslash inside the string, right? Maybe you want to actually quote, like write a quote in your string literal. So you might be like, what's a quote? Can't think of anything. Hello world. Hello. 2025. Like you might want to print something like this, right? Where the quote is in quotes and then some citation. And then because it's a string literal, you want to wrap this entire thing in the actual quotes. But hopefully we understand that this is sort of problematic for a compiler because, well, in its mind, it just sees two quotes here and thinks that must be the string. And then sees another string here, another pair of quotes here, and thinks, oh, I guess that's another string. And then hello world isn't actually wrapped in any quotes, so it's like, what the hell is that doing there? So yeah, this is problematic because, of course, we know what we want. We want these quotes to be part of the string, and these to just be the enclosing quotes. But in order to tell the compiler what we want, we typically use a backslash. So we would actually do something like this. We put a backslash between the two inner quotes here, and we call this an escape sequence or something. So the backslash, the blue backslashes are used to escape the character. Escaping basically meaning taking away any additional functionality, purely making them cosmetic. So the backslash escapes the quote here, meaning it's just a quote that to look at. It doesn't actually have any additional meaning in terms of like enclosing any strings or anything. So that's what the backslashes are for. And similarly, if you wanted to do a backslash inside your string, let's say for example, you would do two backslashes. So something like this, maybe like this. I'll go like this. So imagine you want to print one backslash. Because the backslash itself is a special character with special functionality, trying to write a backslash by itself, the compiler's going to be confused. It's going to think that you want to escape the character, but then it's thinking, well, what character do you want to escape? So to make it purely cosmetic, you actually use another backslash to escape the original backslash. So that's just another example. But backslashes in non-raw strings are purely for escaping characters. I forgot what I was talking about. Sorry. Yeah, backslashes in non-raw strings are for escaping characters, taking away their extra functionality if they have any. Now, this can get really annoying if we have a lot of quotes or a lot of backslashes or a lot of anything. Maybe I don't have to explain what regex is, but I will say that regex strings are strings that typically have a lot of like square brackets, parentheses, I think, a lot of numbers in there as well. Other things. There's a lot of special characters in regex. So when you make a regex string, so in that sense, we might often want to, and I believe the backslash is actually used. Now I think about it, maybe quotes are used too. No, backslashes are definitely used in regex. So you can imagine if you want to do one backslash in your regex, you'd actually have to put two backslashes in your string literal in order to represent one backslash. I'll put an example, but I don't know if it'll be super helpful. But yeah, in general, the important thing to take away though is that trying to do this backslash quotes, backslash, these kind of escape sequences, if you've got a lot of them to do in one string, can get really annoying. So a raw string literal makes all characters purely cosmetic. So, no character has any extra functionality. That says makes all characters purely cosmetic. Sorry. There's no extra functionality in any character. And what we do is we have a prefix of capital R. So we might have something like string s equals capital R, then our quotes. And then we might put like some weird things in there. Backslash, quote, quote, like that, for example. I'll do it in red just to make it super clear. So R, quote, quote. So by doing R, quote, quote, everything inside there is going to be nice and clear, because what the compiler knows then is I just need to look for the lastmost quote, and that will be the sort of enclosing quote with my first quote next to the R. That's how the compiler can kind of interpret that. Apparently, raw strings can contain new lines in them. It's like a random note I have on the side. But raw strings can contain new lines in them. So I believe what that means is if you literally were to write string s equals, and then do R, quote, and then start typing away, you say, hello, my name is, and then you go to hit the enter key, and then start a new line, and say Bob, and then do a quote like this. The raw string, with a capital R, would actually reflect that new line. It would detect that there is a new line in there, right? Typically you write it with a /n, but for now you can just imagine there's a new line that causes that. It will know that there's a new line in there, an enter key in there, and will reflect that. If you were to, for example, print s, it would show that there's a new line, print it with a new line. If you were to try this with a regular string without the R, I think it's a compilation error from memory. It's just not something that happens. It's not allowed. So raw strings allow for new lines to be just used. And yeah, the common purpose of this is regex. I guess that's the only reason why I wrote that there. But you can still understand without having a foundation in regex. But usually, if you're going to write a pattern in regex, it's nicer to use raw strings than regular string literals. Okay, now we get to 7.3.2.2, which is larger character sets. We talked about this a little bit in the character section on chapter 6, because we're talking about sort of using characters beyond ASCII and things like that. I think this particular section looks a lot at Unicode from memory. So again, if you don't have a solid foundation, if you don't know how Unicode works, I don't think it's a huge deal, but it might take away a few details. It might not be quite as obvious exactly why we need these extra details, I suppose. So imagine you have a string with a prefix of L. You might remember that we had wide characters in chapter 6, where again we used the prefix L, but for character literals. This allows us to use wide characters, so characters that aren't on the ASCII table, but are otherwise defined. So the example here is angst. Apparently, we put an L on the outside. Now angst you could actually do without the L, because they're all within ASCII. They're all within the original character set. But you can imagine instead of one of these characters, you could replace them with something outside of ASCII, and that would be kind of, the L would basically allow those characters to be in the string literal. So yeah, string with a prefix L is a string of wide characters. The type defaults to wchar t array. So you might remember that for a wide character, the type defaults just to wchar t. That is wchar t. When you have a bunch of them in a sequence, though, they become an array. Right, so each one of these individual characters here, even though they're all part of ASCII, would all be of type wchar t. Right, so they might take a bit more space, more than one byte. You can actually combine the two prefixes we've seen, L and R. You can use prefix L and R together. Right, so for example, L R quote angst. Oh, I messed up. Okay. Okay, something to mention. I'll try to cut this around a little bit to be a bit clever. Something I forgot to mention about the raw strings. When we did the example string s equals r quote bracket backslash this one, this, and then this. So yeah, that's fine. We have something that looks like this. It's both the quote and the bracket that starts and ends the raw string. So for example, in this case, the string that gets read off is actually just backslash quote quote backslash. The quote and the parentheses pair sort of start and end the raw string. That's the general default. Yeah. Okay, should be fine. I'll put that in front, and then I will do clever editing to get back to this. So maybe I'll get rid of this aside again. We can also combine the prefixes we've seen so far. So if we have so the string with prefix both L and R, right? We can do something like LR quote bracket and then angst, like that. And essentially we have a raw string, right? So looking inside there, that's our string, but with wide characters, right? wchar characters as opposed to regular characters because we use the L as well. So you know, we can combine something prefixes in that way. And these strings here are terminated by the null character again, but it's a wide character. So I'd write it like that. Right, so this null character, even though it could take 1 byte, right, because we don't need more than 1 byte that's on the ASCII table, probably would take more than 1 byte typically, because wchar t is usually bigger than characters. Than the regular character thingy-majiggy. The regular character type, the regular char type, yeah. Using wchar t usually takes up more size than the regular char type. That's what I get at. Alright, so I mentioned Unicode, I think. So we were actually able to use specific Unicode characters. You can think of Unicode, if you have no sort of concept of Unicode, the way I would think about it is think about the ASCII table, then think of a really big table where, you know, instead of 0 to 127, it goes into like, I don't know, the millions or something. I don't know, actually I don't know, maybe thousands, tens of thousands. And essentially it's for all characters like other languages and emojis and like a lot of random symbols and stuff. So all those characters are now sort of part of the character set. That's what Unicode is basically about. It's a specific type of larger character set. So if we want to use Unicode specific characters, depending on your type of encoding, and encoding is a bit scary, but there's essentially 3 types of Unicode encodings. They all use the same character set, but it's basically different ways of representing the same numbers. this requires a bit more further investigation, understanding what each of these are. So what I will say is UTF-8, I believe, is usually the most common. But for now, again, this particular specific section is probably more people who are likely to actually use Unicode in the near future or in the future. So UTF-8 is terminated by a UTF-8 string is terminated by the null character, like our regular strings. UTF-16 uses a UTF-16 version of the null character, so a lowercase u, and UTF-32 uses uppercase \O, like that. And I believe we talked about the lowercase and uppercase u prefixes in chapter 6 in the character section. I hope I did. But essentially, the lowercase u means use 16 bits, I think. And this means use 32 bits. Yeah, that's got to be. There's no way 32 bytes. That means use 32 bits, which is kind of in line with UTF-32, and it's the same use 16 bits, which is pretty in line with UTF-16. So that's all that is. That's what that prefix is for. And then the non-raw prefix to use each of these encodings. You've got U8, U, and capital U. So U8, which is very similar to the U, which is the lowercase version of that capital U. So if you wanted to use a string that used Unicode, specifically the Unicode with UTF-8 encoding, you would prefix it with U8. If you wanted a string literal that used Unicode characters, specifically using the UTF-16 encoding, you would use lowercase u, etc. And the raw prefix is basically the same thing, except with a capital R after it, raw prefix. So if you want to use a raw string that's also using Unicode characters, you would basically do the exact same thing, but then with a capital R after it. So UR, capital U, capital R. Okay, the rest of the notes do go into a bit more detail about like how Unicode is typically written. How do I want to do this? I'm trying to like balance between like going into a lot of detail and not going into detail that's like a bit too far beyond C++. So I've come to the executive decision to basically finish talking about Unicode here and larger character sets here. I think what I'll do is I might make a separate video on Unicode itself and then tie that in with C++ syntax. So we'll talk about more about using these prefixes, but in essence, if you are comfortable with Unicode strings already, these prefixes let you create strings using Unicode characters, essentially. String literals using Unicode characters. But that's all I'll say about that for now. We'll move on to more sort of generic C++ things that don't really require as much prerequisite knowledge. In fact, we finished with 7.3 about arrays, and we moved to 7.4, which explores the link between pointers and arrays. So pointers, in fact, two arrays. All right. Now, I talked about the implicit conversion that can happen from an array to a pointer, where that conversion basically takes the first element of the array and takes its address and uses that as the value for the pointer. So the name, just want to make sure that's big enough. I'm going to consciously try right bigger. The name of an array can be used as a pointer to its initial element. So I have a code snippet. Imagine we make an array like int array. I'm not going to bother giving an explicit size, but I will say 1, 2, 3, and 4. Right? Remember, in memory, in reality, each grid cell represents 1 byte. For this instance, we're just going to pretend that each grid cell represents 4 bytes. Okay, so 1 would be stored in 1 cell, right? Because we're pretending it's 4 bytes. Then 2, then 3, then 4, and the array would be kind of over there. The array would be that's not good. The array variable would be associated with that first. The array name would be associated with that first element. Okay, 1, 2, 3, 4 in memory. So if I was to then try initialize a pointer to an integer, so p1, int star p1, if I was to initialize a pointer to an integer, and I was to use the array name, that's actually perfectly fine. What would happen is the address of the first element, the first byte of the first element, right, because this is actually made up of 4 bytes, so that first address there, that's not good. I just broke that into 4 sections because there's 4 bytes in there. But the first byte, the address of that first byte would be used as the value for p1. Okay, so that second line of code would trigger an implicit conversion from array to pointer. Okay, this is equivalent. What's happening in that second line is equivalent. What's happening in that second line is equivalent to if you were to do int star, I'll say p2 this time, equals ampersand v naught. Let's remember what each of these operations do. First, we will do this operation first. We have v, oh no, not v, sorry, wrong name. ARR v naught, sorry, of naught. Maybe butch that one. So we're taking the 0th index of the array ARR, which means we're taking that very first element, right? That very first element, and then we're doing the ampersand operation, which means the address of operator. So we're taking the address of where that first element, that 0th index element, starts. We're taking that address. So we're going to take that address and we're going to assign it to the pointer p2. So this is kind of an implicit conversion. This is kind of like the explicit conversion, really writing out exactly what's happening when you want to assign an array to a pointer. We're taking the address, the starting address of the first character in the array. Right? So that's kind of the relationship. Sorry. That is the relationship between arrays and pointers. Arrays can often be converted into pointers in that fashion. However, going the other way is a little bit more tricky. So we'll just keep that for now. So I'll just mention that implicit or explicit conversion from pointer back to an array is impossible. And so purely using the pointer that you created, you cannot get the array back because the information about the array size is not given. So to the pointer. So the pointer alone, of course you might know what the size of the array is because you specified it. So in that sense, you can sort of figure out how many addresses you have to look at in memory to get the elements you need. But the pointer alone, without using the extra information of the size, the pointer itself doesn't know about the size of the array. It just knows where the first element is. So the pointer alone is incapable of being converted back into the array because it doesn't know the size. Sorry, I forgot what I was saying. Yeah, it doesn't know the size. So going backwards, going from pointer back to an array, we cannot do. Now, something to mention, obtaining the address of any element in an array is defined. Hopefully that's relatively intuitive in the sense that, well, maybe I'll write it like this. Before I wrote p2 equals ampersand v naught, right? Let's say that, oh, sorry, I keep using v for some reason. ARR 0, like that, right? That was the example I used before. We used 0, but let's say, we have, the list looks like 1, 2, 3, and 4. It's perfectly valid to get the other addresses, 0 would get me the address of the 1, index 1 would actually get me the address of the 2, 2 would get me the address of 3, and 3 would get me the address of 4. Right? It's very valid to do that. We can get the addresses of any of these elements that exist in the array. That's perfectly fine. Now, the thing that might not be as obvious, and this is sort of something that was decided when C++ was being developed, is obtaining the address of, I'll say the position, of the memory, of the byte, right after the last byte in the array is also well defined. It's also defined. I'm not sure how clear that is, so I'll probably draw it out. I think that makes life a bit easier. I'll get rid of the first 2 points just to make space. So let's say I have, I'll probably try to be really explicit about the bytes. So let's say, I'm not going to bother doing all the grids, but let's say I have, again, 4 elements. Oops, that's way too long. Okay. And then, of course, in reality, we would have our bytes afterwards. So I've drawn these longer rectangles, and I'm going to break them into 4 bytes. 2, 3, 4. I'm going to use red just to make it really obvious. So 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4. Right. So in terms of the array, 1, 2, 3, 4. This is an integer array. Maybe I should have said that before. This is an integer array. So each one of these elements is going to take 4 bytes, or 32 bits. So that first element, I'll just make this really dark to make the borders really obvious, because it's not clear, I guess. So that the element 1 is going to take up 4 bytes worth, right? 4 grids. That's the element 1. Then the element 2 is here, the element 3 is here, and the element 4 is here. And I said getting this address is fine, right? We can access that address. Same with this one, right? It's the first byte of this element, so we can get that address. Same with this one, and same with this one. That's what we just talked about, getting the address of any element in the array. What this second point is saying, took a bit of time to get to it, but what the second point is saying is getting this byte as well, that is the byte right after the last element, getting that byte is also defined. Why is that helpful? I will see that in a second, but essentially it lets us find the endpoint, or where the array no longer exists. It's a nice address for that. To be fair, I don't think you have. I feel like there are alternative ways of figuring out what the endpoint of an array is, because generally speaking, you'll know the size. But it's just nice to know that you can obtain that address, and that is well defined. You wouldn't do this. Maybe I might have to interject later about how you actually get that address, because I don't have it written down. But I believe it's through something called pointer arithmetic, which we'll talk about very quickly, but for now, just know that getting that address is okay to do. And then the last point is obtaining any other address outside the array is undefined. So and it's something you should avoid. So trying to get the address of this byte or anything along here, anything before this one, is a problem, right? So we wouldn't try to do that. But any of the bytes that are with an X, or the one that I colored here, you can get that address, and that's well-defined behavior. All right. So now we talk about navigating arrays. And I don't have any code examples written down, which is a bit silly of me, but I'll just write about it and then I'll put it on the screen afterwards. So this is 7.4.1 navigating arrays. So the way we navigate arrays, and if you're comfortable with for loops, and this is something that should come quite quickly, you can use indices, or like plural for index, I think, using indices, or you can use pointer access. I'll try to write through the code, but I will probably write it wrong. So I'll have stuff on the screen. But essentially, if you think about a for loop where, well, maybe I'll start with an array. Imagine you have an array that looks like int r 3 equals 1, 2, and 3. What you can do is say for int I equals 0, I less than 3, I plus plus, or plus plus I. And then you can say, print r at I. So real quick, if you're not comfortable with the for loop notation, we're saying take this variable I, and we're going to start it at 0, and we're going to increment it. That's what the plus plus I does. We're going to increment it until it reaches 3. And every time we increment, we're going to run, and for each value of I, we're going to run this command, print. I've pseudocoded that, but we're going to print the array at the ith index. So it would print 1, then 2, then 3, essentially. So that's one way of accessing or navigating the array, right? We use the index, right? Using the indices, we scan through all the valid indices, 0, 1, and 2, right? Once we hit 3, when this condition I less than 3 no longer is true, so we kind of don't run this code anymore. But yeah, this is a very classic way, especially in C, to access like elements in an array. The other way is via pointers, and this is where I'm a bit less comfortable. But I believe it will look something like this. If you have int star p equals ARR, right, because of that, we'll do the implicit conversion of taking the first element's address and assigning it to p. P is it less than? Or? I'll have it on the thing then. There'll be some condition, and then you would increment p as well. And essentially you would say print, and then you would dereference p. I forget what this condition is, I'll have it on the board, but essentially you get the address and you increment through each address, right? At this address, and this address, and this address, you increment through them, and then you dereference. You dereference here because you don't want to print the address, you want to print the value at that address, at each of the x's. I missed that. Each of these addresses. So then we use the dereferencing operator to actually print out the value. And that's the other way of using pointer access to access each of the elements. Now, we talk about pointer arithmetic. I'm annoyed that I can't remember what the condition is there, but I'll figure it out after I put it in. Do I still want this diagram? Maybe I do. So, I kind of showed it in that for loop there, but we can apply arithmetic operations to pointers. And the act of doing this is called pointer arithmetic. Something that's really interesting is if I have some address p, when I have an address p, right, and I do +1 to it, so like this is a pointer and I do +1, it's quite, how do I say, it's quite reasonable to think that, for example, if p starts here, it's reasonable to think that p would, if we add 1 to it, would point to the next byte. So if I was to do p equals p + 1, it's quite reasonable to think that p is going to point to the next byte. However, because we declare p using a type, right, we say t star p equals blah blah, right? We are given a type t star. We don't just say it's a pointer. We say it's a pointer that points to an object of type capital T. Because we do that, when we do p equals p + 1, the compiler knows, or the compiler reckons, that when we say this, we actually want to jump by a value that is the size of t, right? Doing p + 1 in this way won't increase p by 1 byte. In this case, for integers, it'll increase it by 4 bytes. Because the purpose of pointer arithmetic usually is to scan across an array of elements, right? So when we do p + 1, what the compiler reckons we want is to actually look at the next element. So in a clever way, by knowing what the type is and knowing its size, it will jump by that many bytes, the appropriate number of bytes to get to the next element. So p + 1 will actually jump by 4 bytes in this case for integers, because the size of an integer is 4. So it will jump by 4 bytes to get to the next one. And so, in a sense, you can argue p + 1 is a bit misleading because you're actually increasing p by a value of 4. The address that's stored in p is actually 4 bytes bigger than the previous address. But in that sense of it's the next element. It's the next element that that p is pointing to. That's what that p + 1 is really representing, and that's what happens. So that's a big reason why we need to say explicitly what type of object p points to, because then it can do this jumping. And that's another way that void pointers can be a bit tricky, because if you don't know what the object is, you don't know how much to jump if you've got to do a pointer arithmetic. Yeah, so p + 1 is size of t bytes after, so that's that jump. And then the typical operators. Plus, minus, plus, plus, and minus, minus. And if you're not super comfortable with these 4 operations, so plus, minus, plus, plus, minus, minus, plus basically lets you add some value to p, but you have to make sure to reassign it to p if you want to save that value. So that's an equal sign. I don't know how obvious that is. That's an equal sign that sort of reassigns the p + 1 back to p. Minus is similar, right? If you did p minus 1, in this case, you would go back one element, but you have to make sure to reassign. That's different to plus plus and minus minus. Plus plus, doing p plus plus is equivalent to p equals p plus 1. It increments the value of p by 1, right? Or at least goes across by one jump. And minus minus, p minus minus, is kind of equivalent to doing p equals p minus 1, right? The only difference, cosmetically, is you just don't have to put an equal sign. When you do p plus plus, the compiler knows that you want to sort of update p with the new value p plus 1, and the same thing with the minus minus. There is a way you can go plus plus p and minus minus p instead of p plus and p minus minus. With the operator in the front, I believe that's a very low-level detail, as in not unimportant, but rather like really like the differences between p plus plus and plus plus p are very like high detail and like very nitty-gritty. So I don't actually know the difference off the top of my head. I might put it in, but that's more of something to look at maybe in the future, rather than being too concerned with that. But generally speaking, these are the sort of operators that you can use. However, you cannot add pointers together. Adding pointers together was deemed to be not a super helpful thing to do, in the sense that there wasn't any real purpose to it. However, so it's interesting because there's actually a library, I believe, or a function in the library, I can't remember exactly, called point difference or something, or pointer difference. You can actually find the difference between two pointers, because doing so usually lets you find the number of elements in an array. If you get the very last element, the very last address, and subtract off the very first address, that normally tells you sort of how many elements there were in an array. So there are methods of finding the difference between pointers, or the difference between addresses, but you cannot add pointers together. So you cannot add pointers together. Next thing to note is complicated pointer arithmetic should generally be avoided. Pointer arithmetic is one of those things where, especially, I guess some people might not ever use it, right? Because there are, for accessing an array, you can use pointer access and pointer arithmetic, but you can also use index access. So some people might not even be particularly comfortable with pointer arithmetic, but if you do find yourself sort of having to do a lot of intricate pointer manipulation to move around memory, there might be a better way of doing it rather than explicitly using operators. Yeah. Okay, and I guess the last thing, it's kind of abrupt, but it doesn't really have anything to do with pointers anymore. But inherent arrays, or the low-level arrays, the basic arrays that we've been talking about, do not have their size easily accessible. Okay, so you kind of, as the programmer, you have to keep track of what the size of an array is. I feel like I've said this already, but in case I haven't, you have to make sure you keep track of the size of the array. That's different to something like the standard array library. If you do that, the size of the array is actually built in. You can actually access it without having to have a separate variable for it. You can access it within your array object. We can talk about that later, but it's always important to remember that arrays, basic arrays, do not have their size accessible within them. All right, move on. Multi-dimensional arrays. We won't talk about this too much because this is more of a general concept rather than a C++ specific thing. But it kind of leads on to the next bit, so I want to make sure that it's at least mentioned. So, 7.4.2, multi-dimensional arrays. Technically, you can go up to whatever dimension you want, but after like 2 or at most 3, even 3 is kind of crazy, but at like after 2 to 3 dimensions, it can get a bit weird. But what are dimensions when we talk about arrays? When you see the term multi-dimensional arrays, what you want to think about is an array where each element is an array. So normally we're talking about an array of integers. Each element is an integer, or an array of characters. Each element is a character. But here, because array is just another type, so we can have an array where each element is an array. And each of those sort of child arrays maybe has elements that are integers, or elements that are characters, or elements that are arrays, which would make a three-dimensional array. So if you have an array where the elements are integers, that's a one-dimensional array. An array where, an array which with an array with elements that are arrays, which then have elements that are integers, is a 2D array. An array that has arrays that are elements, which has arrays that are elements, which then has some primitive type, is a 3. Like, so you can technically, you can imagine you can scale it up as much as you want, but generally we will talk about 2D arrays. 2D arrays are the ones that we're going to be discussing because that's generally what we talk about. So this means that each, I'll say, I use the term child array, I don't know if that's proper, but each child array contains non-array elements. So very classic, very like simple example. What I'm drawing here, maybe I should use the squiggly lines, squiggly brackets. This is my outer array, right? For my 2-dimensional array, this is my outer array. The elements, which I will draw in blue, the elements inside this outer array are going to be smaller kind of child arrays. That's enough, yeah. So the blue is the child arrays that are contained within the outer 2-dimensional array. And within each child array, there will be some non-array type. So we'll say characters this time. If you're using integers as well, let's say characters. So like A and B, and this one might be like C and D. So each individual child array contains characters, right? C and D. I should draw this a bit bigger. C and D. Is that any better? Hopefully. Yeah. So each child array has characters within it, but then those child arrays are contained within this parent array. And if I had like this and another one of them, and that was contained within an even bigger array, then that would be a 3D array, and so on. But essentially, this what we see here is a typical example of a 2D array. Now, maybe I should do one more. I'll do one more child array just to make things really, just because it'll make my life easier on the track. E, F. Okay. So let's just really, if we look at this particular example, let's just exactly understand what's happening. Let's say I want to declare and initialize something. I'll do it like this. So in this case, we have characters, so it would be char, and then I'll just call it M for the array name. What we typically do is we ask ourselves, well, how many child array elements are there? How many child array elements are there? And well, there's 1, 2, and 3. Right, there's 3 of them. So, in typical fashion, we put something else like this. We're saying M, the outer array, has 3 elements. 1 child array, 2 child array, 3 child arrays. But then we also have to tell the compiler how many elements are within each child array. And that's what this is for. We add another like array operator in our declaration, and that says how many does each child array have? How many elements does each child array have? And hopefully it's clear that the multiplication of these two numbers tells us in total how many char elements there are, because each child array has 2, that's what this number is saying. Each child array has 2 elements, and there are 3 child arrays. So 2 lots of 3 means there are 6 characters total, which then tells the compiler, since we know that the type is char, that we need 6 bytes total, because a char is 1 byte. Char takes up 1 byte, so 6 bytes total. So this information given here is actually enough information to tell the compiler how much memory is going to be required for something like this. Sort of a tidbit. In our minds, we visualize 2D arrays a bit like this, right? With child arrays and things like that. In memory, however, a 2D array is actually unraveled into a normal array. So in memory, 2, 3, 1, 2, 3, 4, 5, 6, right? In memory, and each grid cell there is 1 byte because we're doing characters anyway. It would literally look like this. Like doing, in terms of how the memory looks, using a 2D array or a 1D array, like A, B, C, D, E, F, or like this, would result in the same kind of thing. Just 6 bytes in continuous fashion, where each character takes up 1 byte. I'm on the wrong page. I believe if you wanted to initialize this, right, like if you wanted to give it A, B, C, D, E, F, I believe you could probably use a for loop. I'm not sure if you can use list initializers. I'll check that. But in terms of initializing something like this, I'm sure you can definitely use a for loop, because when you write this, you've allocated the memory. You've allocated the memory without putting any values in there. And then you can use a for loop to basically go through each element. And accessing each element is probably important. Let's say I wanted to access the C here. What would I do? So this is me declaring. How would I access it? Once I've created M32 and I've initialized it appropriately, if I want to access the C, well, I have to ask myself, okay. So I'd say, okay, well, which child element is it in? Well, it's in index 1, right? This is index 0, index 1, index 2. This is element, because this is element at position 0, element at position 1, right? So it's in the first index. And then from there, it's like, well, within that array here, this child array, which position is it in? And well, there's position 0, position 1. So we pick position 0. So we do this. So if we ask C++ to print, again using pseudocode for printing, but if we ask C++ to print M10, it would say, okay, it would actually do a bit more. It would actually have a bit more computation to do, because remember, in memory it looks like this. So when it says when you say M of 1, that tells it that it has to skip this entire thing. This entire element has to be skipped. And so it asks itself, okay, how many elements is that worth? Well, it's one child array, and each child array has 2 elements. So we have to skip the first 2. So skip this one, skip this one. And then we're saying position 0, which means the additional number of elements we have to jump is 0. So that means we just have landed on the element we want. So that would print C. If we wanted to do D, right, if we want to get access the letter D, we would do print. Maybe not D, maybe do F, because I think that's better. We would do 2 and 1. Why 2 and 1? Because F is in the child array at position 2, right? 0, 1, 2, right? And then within that child array, it's in position 1, 0, 1. So we do 2 and 1. And how the compiler would interpret that is it would see the 2 and say, okay, I have to skip the first 2 elements. How big is each element, each child array specifically? Well, I have to skip this one, and I have to skip this one, and then I can get to this one. So that means each one of these child arrays is of size 2. So that means I have to skip 2 4 bytes. So I have to skip 1, 2, 3, and 4, right? I don't want any of those. And then I know that I have to go to position 1, which means I have to skip in position 0. So I have to skip this guy, and then I will reach the correct kind of bit of memory. I would reach the correct bit of memory to access the F and print it out. So when we initialize the array, when we declare an initialize array, we write all these values in, and then if we want to access specific spots, this is the kind of thing we would do, using the classic 2D array kind of syntax. Yeah, okay, so that's just a bit about multi-dimensional arrays. How are we going? Okay, not bad. See if I can get to like 7.5 or even 7.6 today, and then I'll finish it off later. So this next bit is 7.4.3, parsing arrays. So I think we mentioned this, but arrays cannot be parsed usually into functions. Talking about parsing arrays, I mean parsing it as information into a function. I'll write up an example in a sec. Arrays cannot be parsed by value. Arrays are instead as a pointer to the first element. So let's say I have something like void f int star array. Right? And so we'll do a bit of a for loop. I equals 0. I is not equal to 10. Right? Not equal is usually written as exclamation mark and then equal. That's the not equal operator. I is not equal to 10 plus I And what we'll do is we will access the array at the ith index and add on 100. Right? So just to clarify what this is doing, we're going through indexes 0 to 9, right? Because we're not letting I go up to 10. So for I from 0 through to 9 inclusive, we're going to access the element at that index and add 100 to it. And so, for example, we might take in, outside of the function, maybe in the main function, we might have something where we declare an array int a10 equals, and we might it should be on one line. I'm just out of space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what would happen? And then we might call this function f of a. Call f, giving the array a. What's going to happen? Well, we cannot pass the array by value, right? In the sense of we're not going to just throw in all 10 of these values into the function. What's going to happen instead is the data that f is actually given is the address of the first element. So when we do this, we're actually getting the address. And this code still works because C++ is basically capable of interpreting a pointer as an array. So by accessing the memory addresses of the original array, if we were to print this array, print A again, or print the elements of A, then we would actually get each element added up, each element increased by a value of 100, so we'd actually get 101, 102, 103, 104, 105, and so on. Because we didn't pass the array by value. We didn't just give the values. We actually gave the address to this array. We gave the memory address of this actual array that we created here. And so we're accessing the same memory addresses in this function. So when we print A and access that memory one more time, we'll see the effects of function f on this original array. However, there is a problem with doing this, and that is this function completely assumes that the size of the array is 10, because I can be 0 through to 9, which is 10 elements. But if, for example, let's say instead of A10, I made it A5, right, and only did this, right? So this is completely legal, and doing this, passing A into F, is completely legal, because all that would happen is the first element's address would be passed in. So all of this is completely valid, and it would do for int I. Like the compiler wouldn't pick this up at all. There's no real there doesn't seem to be anything particularly wrong here. Not yet, right? You have 5 elements. You take the address, you pass it into here. ARR is equal to that first memory address. But then you start doing this loop, and index 0 through to index 4 is completely fine, right? It will do that, no problem. But then I equals 5. I is still not equal to 10, so we continue. We run the loop, and we try accessing ARR of 5. But that doesn't exist anymore, right? So passing A into the function was fine, but now the function is trying to access something that doesn't really work. And we said that accessing, using the index operator on invalid indices is undefined and problematic. So we have to be a little bit more careful when passing in arrays into functions, right? There's a few ways of handling this. The main way that I would think is trying to basically pass in a size parameter into your function. But I will. So we might, instead of doing just int r, we might do something like int size as well. And instead of I less than or equal to 10, we'd say I less than or equal to size. And instead of just a, we would pass 5 in this case. Right, so for single one-dimensional arrays, we might do something like this, where we still pass in the pointer, but we also give a size variable so that we know how many elements we're allowed to go across before we reach out of bounds. Now, the slightly more interesting case is looking at 2D arrays. So this is what you might typically do for one-dimensional arrays if you had to pass them into a function. The other option, for two-dimensional arrays, you have these different sort of varieties. You have void. Imagine you're trying to make a imagine you have a 2D array, and you want to print each element, the child elements within the 2D array. So not the child arrays, the elements in the child arrays. So you might have something like print, I'll just say m, and you might say int m 3 5. What this is saying is this function printm is only going to take in elements, 2D arrays with 3 child arrays and 5 elements in each child array. That's what this is saying. So this is like the strictest kind of constraints you can have, where you specify both how many child arrays you have and how many elements those child arrays have. Okay. You can actually relax one of the parameters by doing print m int m brackets 5, and then you probably want to give a number of child arrays kind of parameter. So what is happening here is, well, what this is saying is this printm function is happy to take in any 2-dimensional array with any number of child arrays, so long as each child array has 5 elements exactly. That's what this is saying. And then this extra parameter here is just to say, in order to print every element, I need to know how many child arrays there are. So just pass that information in as well. That's what's happening there. So that's also completely fine. Now you might think, well, what if I choose to cut out both of these pieces of information? Like I do something like this: void print m int m nothing and nothing, and then int, and then number of child arrays to know that first number, and then number, and then child array size or something. Child array size. That is how many elements are in each child array. So to give that second number. And you might think, well, maybe this just means I will take in any 2D integer I like. However, there is a problem, right? The compilers. Sorry. What we have to remember is that although we understand that these values here and here are associated with the brackets here and here, right? With the values here and here, the compiler doesn't know that. The compiler doesn't know that these two numbers are associated with the array. So it just sees when it's thinking about the 2D array, it's just looking at this, and it's concerned because in its mind there's not enough information to actually handle this 2D array well. And what do I mean by that? I'm trying to think. I had to, but I still had that other example with the 2D array. But remember how we were talking about accessing elements in that 2D array? We have to think about which dimension was actually really important to be able to do that in memory. So how I'll talk about this is I'll just draw it up really scrappily. It was something like A and B, and then C and D, and then E and then F, right? And then we had child arrays in there. And then we had parent array, right? So we have each child array, and in memory, it would look something like blue. In memory, it would look something like this. You've got our grid, and again, I'm not going to bother drawing the whole grid, but we're going to need 6 bytes. It's going to be like something like this: 2, 3, 4, 5, 6. A, B, C, D, E, and F. Okay, so yeah, let's say I want to access let's say F again. Yeah, let's say we want to access this element here. So in our minds, we would say, okay, well, again, let's call this M. I want M at 0, 1, 2, right? Index 2 for the child array, and then index 1 for the sort of inner child elements here and here, 0 and 1. So that's what we would do, right? How does the compiler know where to look in memory? It looks at the 2. And of course, I should say that M has dimensions 3, 2, right? Three child arrays, each containing 2 elements, right? So 3 and 2. So when we say this one down here, how does the compiler know, or the program know, to access F over here? What's happening? Well, the compiler looks at this and says, I want to skip the first 2 elements. how many bytes is that? How many elements do I have to actually skip? What in terms of memory? It looks at this dimension here, right? It looks at that second dimension and says each one of these guys has a size of 2. So if I have to skip the first 2 elements, if I want to get rid of this one and then this one in order to get here, I have to skip 4 elements total. 2 from here and 2 from here. So 4 elements total. So I skip 1, 2, 3, and 4. And then it says, it sees this one and says, okay, well, now I have to skip element 0 in order to reach element 1. So I'll skip element 0 to reach element 1, right? And now I've reached my f. But in terms of which of these dimensions did I actually use in order to do that calculation, to actually access the right memory? I only used the second dimension. The first one is not actually necessary for this operation. The second dimension is the only one that's actually important for sort of doing that calculation. We didn't really use the 3 there. That's why this function is okay, because I gave that second dimension even though I didn't give the first one. The compiler sees that and says that's okay. But not giving the second dimension here means the compiler is worried that's not going to be able to do the necessary operations such as accessing. So that's why this is completely fine. This is also okay, this will be allowed, but this will result in a compilation error. Because it will see that you're trying to use a 2D array, but it will also think that you haven't given enough information to work with it as a 2D array. So that's something to bear in mind. But what if you really, really want to be able to pass in whatever 2D array you want, right? You want something like this, right? But the compiler is giving you an error. You want to have something like this. What we do instead is we pass in a pointer, right? We just work with addresses. So we say int star p, int, and then number of child arrays, and then int child array size. So we still give the same information here and here, but now we're just passing in the address of the very, very, very first element. So very quickly, I'll just draw it scrappily, but if I have something that looks like this again, and I have element 1 like this, we pass in the element here, right? Maybe we say M00 and then we ampersand, right? Just to be really explicit that we're getting that memory address, right? And that's what we passed into here. And this time, the compiler doesn't interpret this as a 2D array. So that idea of needing to pass in the second dimension is no longer a requirement, and so it will let that run. That will be okay with that. And then we, as programmers, can use this information here to be able to access all the other memory addresses that we want, and dereference if necessary, and I don't know, print the values or whatever. All right, that's 7.4. So I'll probably finish off the rest another time because it's getting late. And I want to sleep. So I kind of realized that, kind of to interject myself, I realized that I didn't explain what passing by value means. It's on my notes, because I think I knew what it was, but I felt like I should sort of try to explain it to make sure I really know what it is. And the context is, well, I'm sure the context is clear in the video, but I don't really, I need to remind myself. I think it's, so arrays cannot be passed, or are not passed by value. And this idea of passing is usually in the context of functions. When you want to pass an array into a function or pass some variable into a function, arrays specifically are not passed by value into a function. Are not passed by value. Arrays are not, what the heck? Sorry. Arrays are not passed by value. So we'll go through like two kind of examples. One where we're passing an integer, and then one where we're passing an array. And we'll explain what passing by value means through that. So imagine I have a function, int f, which takes in an integer x, right? So that's our single argument that f takes in, and it returns an integer outright. And let's say all it does is it returns 2 times x. So it's a doubling function, right? It takes in x and returns 2 times x. And then we have our main function, right? The entry point function, int main where execution is going to start in a program. And imagine I create int x equals 7, and I print the value of f of x in here. And then I return 0, just because that's what we always do, right? So this is our like code. So if we look at what happens, just reading it, it's clear that we're going to have int x, this x value is equal to 7. We're going to pass x into the f function. It's going to come through here. We're going to return 2 times x, so 2 times 7, which is 14. So we're going to return 14 back to here. And so we're going to print the value 14, and then we're going to return 0, which just means, is this recording? Oh, thank God. It just means we're returning 0, just means like everything's okay. But the important thing is we're going to pass x in, get 14 back, and print 14. That's what's happening there. What's happening in memory, though, is a bit more interesting, right? What's happening in memory is a bit more interesting. If this is my slab of memory, each function gets something called a stack frame. I don't know if I talked about stack frames yet, but stack frame is basically a partition of memory that is allocated purely for that function to work with. So no other functions are going to work, like mess around with that memory. And once the function is done, that stack frame, that subset of memory, is going to be released back into the wild kind of thing. So we start with the main function, which I believe will get the very first stack frame. Put in red. So we have something like this. This is like our main function and its stack frame. So what's happening? Well, wherever we need memory, it will allocate. So int x equals 7, in this case, 4 bytes of memory are going to be allocated for this x variable. So this little section here, x, and it's going to be given a 7. Okay. Then we call the f function to be able to print it out. We call it first, which means a second stack frame is going to be utilized. So this is the f function, right? Now we pass this x value into here. Now for ints, for integer types, and I believe basically all the fundamental types, when you pass a value in like this, the value gets copied. There's a copy operation that happens. So when we have this argument or parameter x, we have this parameter x, it gets copied. So it's the same value twice, but there's a copy operation that goes from here to here. Right? Copy operation. So while it's the same value, the memory addresses are different. That's something important to note. Okay? And when we do return 2 times x, we calculate that value, 14. Calculate that value, 14. And then we return it, right? This is kind of temporary memory, we're just sort of writing down. And then we return it back into here. Again, in temporary memory for now. Okay? So, what to note is the x got passed by value, right? It's not the same x. It's not the exact same x with the exact same memory address. The value 7 got copied, and it so happened to be that we use the same name twice. We use x in this scope, and then we use x in this scope. In reality, I could have used a completely different letter here. I could have used like a, and so meaning that this would actually be a. But the value 7 would have still been copied, no problem. It's just a cosmetic difference just in terms of the name, right? And the other thing to note, let's say, let's just keep things as x. Let's say before I double things, I actually increase x by 1. X equals x plus 1, right? So what's going to happen now, 7 is going to increase to 8, right? And then 8 is going to get doubled to return 16. So this will now print 16. Okay? However, even though this 8, this x here got increased to 8, right? And this now became 16. If we were to try to print x again, so we printed f of x, but if we were to print x again, or not again, but if we were to print x, what value would get printed in the main function? Here, x got changed to 8, but we are no longer in the f function. In fact, once the f function terminates, the stack frame associated is destroyed. So even though x got increased to 8 here, if we were to print x, it would still print 7. Because in terms of this, the main function's x, we would look at this x over here. And while the x in this stack frame got modified, the original x did not. So it would still print 7. And that's what passing by value means. It means even if I make modifications, even if I do whatever I want with this value, those changes are going to be reflected in that stack frame with that x value, but the original x value is actually untouched because we did a copy operation. So that's what it means to be passed by value. But now we think about the context of arrays. So instead of int x. Sorry, instead of f taking an integer, let's make it take in some array, right? And let's make x equal. Let x be an array with 3 elements in it. What happens now? So x now looks something like this. And let's say all we do is, what should we do? Let's return the sum of x. I don't know if this is actually, I think this is a thing. There should be a sum function, but just say there's a function sum that exists in standard library, which takes the sum of the array. So in this case, 1 plus 2 plus 3 is 6. So if we simulate what happens here, so I'll get this copy. Main function, once again, creates the array, writes it into memory. Then we call the f function. I'll do this as well. Then it calls the main function, calls the f function. So we create a stack frame f. Okay, and we're going to return the sum. Now, is there a copy operation? Last time when we passed in the argument x, and we had this parameter x, we did a copy operation. But this is where this fact comes in. Arrays are not passed by value; they are passed by address. The actual value of x here, under the hood, is the address. It's the address that points to the very first element of the x array, right? So under the hood, this x is actually a pointer that points up to the first element. But C++ is smart enough, or is able, like the compilation is able to handle the translation of pretending it is an array, right? When you ask to use it as an array, like let's say try to index, maybe you print x at index 1 or something, or 0. Let's say you want to print the very first element, which kind of assumes, which means, maybe I should say 3, just to make it really careful. Let's say you want to print the very first element. You want to make sure, what happens is, even though this is a pointer, right, because it knows it's a pointer that points to an integer, it knows sort of where that first element lies in memory, so it can print it anyway, even though this isn't strictly even though it isn't strictly an array. Right, it's actually a pointer. It can still access the memory addresses. You know, if you try to print 1, again, because it knows that each element takes 4 bytes because it's integer type, it knows how many bytes to skip over in order to reach the element you want. Okay, and then so in similar fashion, you return sum of x, it figures it out, figures out the value, figures out it's 6, and then returns it back. When the function terminates, all of this is gone, but notice that the address is gone, but the array still persists. And the other thing to mention is if you do modifications, right? If you if instead of all this, all you do is say x at 0 equals 7 or something, right? Because the x here is an address and not a copied, not the copied values. It is actually the original x that gets modified, right? Originally, it is the original array that gets modified because we're using the address. So when we do x0 equals 7, it's actually the original 0 index that gets changed to 7. So we print f of x here, which would be 6. It would change actually because we've changed this value. The value here, the value returned would be 12 because after we make the 7, we do the sum operation, and this would return 12 back. Then this would be changed. This would be destroyed once the function terminates, and then we print this value, which we said was 12. So we print 12. But then if I try to print x at 0, right? Before, when we printed something from the original object, we didn't see any changes, right? Because of that copying. But now we are doing the copy. This would actually print 7. The changes from function f are actually reflected in main, right? The changes persist. That's the difference with passing an array by address and not by value. Okay, those are the major things. And the reason for doing it this way, without doing the copy operation, is once again, copy operations are generally expensive for larger data types. So arrays, for example, which consist of many elements, maybe hundreds of elements, thousands of elements. If we did a copy operation, we'd have to copy every single element down, and that would be costly. So rather, we just pass in the first memory address. So that is a bit of explanation with like functions and stacks, memory stacks. Function stacks. Wait, what's the terminology? I think it's function. Yeah, function stacks. Little sort of boxes of memory, and what it means for arrays to not be passed by value, and why that's a good idea. So yeah, that's just like I'll put it like, I don't know, I'll try like slip that in without too much hassle. All right, so now we move to 7.5, where we look at the keyword const in relation to pointers. So I think we've talked about const a little bit, but I think the first thing to talk about is what is the point? What is the purpose of const, the keyword const? So there's two related meanings for of the term constant, right? We think about constants in programming. We think of two sort of things. There's the const expression, right? This is one keyword we can see, and this basically means evaluate a constant at compile time. So if you ever see something get declared as a const expression, it's telling the compiler to figure out the value of that constant at compile time and maintain that value throughout the runtime. And then the keyword that we're going to be looking at, const, essentially means do not modify this particular variable in this scope, or within this scope. Within this scope. So we're primarily going to be looking at this one. So this idea of not being able to modify a value is the purpose of the const keyword. So why is this helpful? Many objects will not change their value after initialization. So you think about, we talk about strings, that's one place, the string literals, I should say, one place where we mentioned const. String literals have the type const char array, because you think about something simple like a hello world program which prints hello world. You have something like int main, and then you print hello world. That string isn't getting modified at all, and there's a lot of instances where things like strings and other objects don't get modified. So it's quite helpful to label them as const because they shouldn't be modified anyway. So if you ever have a variable, some kind of variable that you're not planning on ever changing in terms of its value, declaring it with the keyword const at the front is a good practice. So in essence, to express immutability, add the keyword const to the definition of an object. So immutability basically just means the value is unable to change, whereas mutability means the value of the object is able to change. To express, So for example, we could do something like const int x equals 4. So this would be our normal definition. This is what we normally write. And then the const means that x, the value of x is never going to change. So if we try to write something like x equals x plus 1, right, reassign the value of x to an increment of 1 by increasing x by 1, giving the value 5, this would cause an error because we're trying to change the value of a constant variable. Const objects must be immediately initialized, so const objects must be initialized immediately, because, like we said, you can't after the declaration line, you're not going to be able to give a new value. So if you don't give a value at all, right, then trying to then say x equals 3 afterwards sort of doesn't make sense for a constant, because the idea is you shouldn't be able to do any kind of reassignment. So whenever we see a const, there's an expectation that a value should be associated with it immediately. So you always want to make sure you have the value immediately. So you want to immediately define your constants. And the const keyword does modify the type. The const keyword does modify the type. Not in terms of how many bits are associated. It's the same size. Size doesn't change, but const int is considered a different type to just regular int. They're very similar in the sense that they both store an integer and certain it's 4 bytes and all that. But const, the act of not being able to change a value, changes the actual type of the object. All right. Now we're going to talk a bit more in detail about const in relation to pointers. Because you can get there's kind of two ways you can interpret a constant pointer. Because a pointer stores an address, but that address then is associated with a particular object. So, pointers. Declaring a pointer as const means the object being pointed to is constant or immutable, rather than the pointer itself. So, imagine we have a char. Right, so we declare a character like this. Char C equals character A. Right, so we declared and defined a character. And then imagine I do const char star, so I put that const keyword, P C equals ampersand C. So in memory, you have the C and the C label with the character A, and then you have the PC variable, which is a pointer that points to A, like that, right? So the value in here is the address of this byte here, right? So what does this const do to modify the type? If you were to try change the value of this in this memory using the pointer, that would cause problems. So if you were to say dereferencing PC equals B instead of A, so you dereference, you travel along the path, and then you try to change this to B, that would cause problems because we declared this as a const. Trying to access the address and then change the value in this way by dereferencing is not allowed. However, just to clarify, you could say C equals B, right? This C variable you could make equal to B because that wasn't declared as const. So this, I believe, would be fine, right? But because we put const in front of the pointer declaration here, trying to change the value in this memory via the pointer would be problematic. However, changing the value of the pointer itself, that is what the pointer actually points to, is completely fine. We could say, if we were to say PC, the pointer itself now points to, or maybe I'll say char, I'll make a new char, C2 equals G, so there's this new thing here, C2, and that has the character G in it. If I was then to say PC equals ampersand C2, this is perfectly fine, because the const refers to not being allowed to change the value via dereferencing. That's what this const is for. Changing what address PC actually stores is not a problem, so this works fine. Changing what PC points to is completely fine. Okay? It's just you can't change the value you can't change the value that PC is pointing to. Now, what if you wanted to make the pointer's address immutable? That is, you didn't want to be able to change which thing PC was pointing to. Then, in that case, we would put the const after the star. So normally we declare like char star PC equals ampersand C, right? This time though, we would say char star const PC equals ampersand C. And what does that mean? That means, I'll get rid of the C2 now. That means PC points to C, and PC is now not allowed to point anywhere else. It's always going to point to that address there. So I guess, how do I do this? Yeah, so if I try something like, again, char C2 equals D, and then try PC now equals ampersand C2, so C2 was here. If I try to reassign where PC points to, that would cause an error. However, if I instead try to dereference PC and make it equal to B, that is, I go via this pointer, I go to this memory and then change it to B. Oh, it was originally A. If I then try to change that to B, that would be okay. Because again, this const, rather than referring to keeping this memory safe, now prevents the PC from changing. So this is fine. Okay? And the last thing we could do, so I guess so far we've had these two cases. We've had const char star PC equals &c. We've had char star const PC equals &c. And the last case is you can combine the two. You can combine both const uses. You can say const char star const PC equals &c. And this means you cannot change the value of c, the variable c. You cannot change its value via the pointer. And you cannot change what PC points to. So by using const here and here, both of those restrictions are applied. And the way that it's like a trick to remembering these definitions is you read the line backwards. So you say, PC is a pointer to a char that is constant, kind of thing. So if the char is constant, trying to change the character through PC is not going to work. And similarly, you can try PC is a constant pointer that points to a char. So constant pointer meaning the same address. It's always going to look at the same address all the time. You can't change what address it looks at, but the char itself is not constant. The char itself can be changed via PC. And just to clarify again, for this first case where you can't change the value of the char via PC, you can still change the value of the char using C directly. So in that first case, you could still write something like C equals Z, and that would work fine, even if you had written this as well. Even if you had this first case, writing this would still allow this to happen because C, the variable C is not the variable C is not considered constant. So you can change it through C, but you can't change it through PC. Okay, cool. Object that is constant. There's one action that is allowed and one action that is forbidden. So what is allowed? You can assign the address of a non-const variable, like that char C from before, to a pointer to a constant. That is to say, it's about that first case. So if I have const char star PC equals &c, that is us assigning the address of a non-const variable, right? C wasn't const, assigning that to a pointer that points to a constant. That's what this line is saying. This is perfectly fine, as we've discussed. However, that is not, so what's forbidden? What you shouldn't be doing is assigning the address of a const variable to a non-const pointer. So, or rather a pointer that points to a non-constant or a variable. So imagine if I was to say, const char C equals the letter A, and then I was to try char star PC equals &c, this is problematic. Because without any constants written down here, it seems implied that we could change the value in the memory associated with C. We could change that value using PC. But this const up top tells us that the value within the memory associated with C, that A value, shouldn't be changed. So this is dangerous behavior. This is dangerous to do. You don't want to be providing sort of non-const pointers to point to variables that are constant. Okay? And it is unwise to use explicit casting to remove constant restrictions. Generally speaking, it's legal to be able to, to cast the C, to convert the type of C, to go from const to non-const. You can do that, but it's considered unwise because if you're going to call something constant, it's probably a very good reason to call it constant. And so to just remove that restriction just to make a pointer point to it without making the pointer constant is not considered good practice. All right. Next, we have 7.6. which looks at pointers and ownership. So we sort of briefly, like in chapter 6, I think, when I was talking about the move operation, we kind of briefly looked at how pointers can correspond to ownership. But we begin by defining the term resource in C++. So a resource is something that has to be acquired and later released. So this idea of you can acquire some sort of resource and then you can later release that resource. So typical examples are memory, right, or objects in memory, but memory in general can be acquired to store a particular object, typically using a keyword like new, and then released using the keyword delete. So these two keywords lets us very explicitly obtain memory to store a particular object, and later clean up that memory, removing that object using the delete keyword. Generally speaking, when we do handle resources and think about trying to obtain it and later releasing it, resources are usually via a pointer. Right? Because you think about, for example, the memory that you acquire, you generally handle that memory and work with it using the memory address, which will be stored in a pointer. Now, there's nothing in the type system that differentiates between a pointer that owns a resource and a pointer that does not. And all that means is, in terms of the type system, what the type of pointer is, owning a particular resource does not change your type at all. You could have two pointers that are both pointers to integers. One might point to a particular memory address that stores the integer 5, in which case that pointer you could say owns that 5, and it sees it. But there's nothing in the type system that allows you to differentiate between those two pointers, where one points to that 5 and one does not. So that's one point to think about. Now, it is usually a good idea to handle resources in a resource handle class. Resource handle class. These are classes that are available in the standard library, and we've seen a couple of them before, but things like the vector library, strings, right? There's a string kind of, not exactly, it's a string that's kind of, the string functionality is kind of within the IOStream library. So I'll just say IOStream beneath it. That's the library, but string is the particular object or the particular class that we work with. And unique pointer. I don't think unique pointer is the library name, but it's again another class within the standard library that is capable of handling resources. And what resource handling classes are capable of is essentially ensuring that pointers are only released, or the resources that a pointer is associated with is only released when there is no more sort of ownership. There's no more need to use that pointer. So when that pointer is when that resource is no longer mentioned in the program, when it goes out of scope, then the resource handling class can knows to destroy that resource. And chapter 13 discusses resource management better, in more detail. So that'll be something that we look at in a lot more detail. Now we conclude with 7.7, but unfortunately 7.7 is still quite chunky. There's like 8 pages associated with 7.7, so you might be here a while still. 7.7, and we talked about references. So we've talked about pointers, we've talked about arrays, and now we're on the last bit regarding references. So pointers, we have seen, lets us pass into functions, for example, potentially large amounts of data at low cost. So, for example, with an array, if you were to pass an array into a function, what's really happening under the hood is it's not that all the elements of the array are copied and passed along to the function. In reality, just the address of the very first element is passed to the function, and then using that address, we can try to access the first element and all other elements after it. So pointers, basically, so in this context, we avoid copying, right? We don't copy every element. We don't copy every element to the function. We just give that first address, and we so simply pass an address, which is cool. However, we have to be a bit careful with pointers. Pointers have a bit of risk associated with them. We might accidentally, we might be dealing with the null pointer, right? Remember, I hope I said this, but the null pointer is something that cannot be dereferenced because there's no value that the null pointer actually points to. It points to an address that is reserved to not have any value ever. So if we're dealing with the null pointer, for example, dereferencing is undefined behavior because there's no value to access. And if we have to be really careful on that, we might point to something, to an object that is unexpected. Especially as we get into sort of more complex programs, you might have certain objects where you don't necessarily know their type very well, and pointing to that object, you try to dereference it, it might lead to something unexpected. And when we overload an operator, which is sort of not exactly introductory, but essentially we can give definitions to, we can sort of make custom-made operators and give custom definitions to them. When overloading an operator, we'd rather use the operator on the object that is being pointed to, rather than the address of the object. Because when applying an operator onto a pointer, we have to always remember to first maybe dereference the part of that operation. So it might have to be dereferencing the pointer first. So it's much cleaner if the operator can just be directly applied to the object in question. So the kind of drawbacks of pointers are covered or improved on by references. So references were implemented in the language. They're a language mechanism, but references were implemented to try remove these shortcomings. So it's good to think about references, like even to understand that these points are the drawbacks of pointers, then means to understand that references were an attempt of sort of removing these drawbacks. So references are an alias for an object, right? Another name for an object. And usually, in terms of implementation, references are implemented to again hold the memory address of an object. So in this way, in the second way, it's actually it kind of shows that references and pointers seem quite similar in the sense that they both work with and store the memory address of an object. That says, oh, the light's being annoying. References are an alias for an object, that's what that says, and then usually implemented to hold the memory address of an object. So both pointers and references work with memory addresses. So then what's the difference? Right? What are the major differences? The major differences in general is that with pointers, the compiler expects that you are working with that address directly. When you mention a pointer, it thinks you're talking about the actual memory address. But with references, the compiler assumes that you actually want the object every time. and so will implicitly, it essentially implicitly does the dereferencing for you without you having to do it explicitly. So you can access a reference using the same syntax for the name of an object. So I think we'll see examples in a second, a little bit later. But essentially you will see that the syntax for accessing and working with a reference, it's as if it wasn't a reference. It's as if you just were working with the object in general. So same syntax. That's different to pointers where you have to actually explicitly dereference before you can start using it. A reference always refers to the object to which it was initialized. So pointers we talked about previously, that pointers you can change what it's pointing to. References will always refer to the same object. And there is no null reference. There is no null reference. So the risk of accidentally dereferencing a null pointer, you can't really, there's no real equivalent to that because there's no such thing as a null reference. You can always assume that a reference points to a legitimate object. So then, what are the main uses of references? When would you likely see them? So the uses or the purposes. Specifying arguments, right? We talked about pointers are really good for arguments because you don't have to pass in all of the, you don't have to copy all of the data. You just pass in a memory address. So references, in the same way, you can kind of prevent too many copy operations. Specifying the return values of functions. So if you think about the function return type that you had to the start of, starting to fade out, I might just get the other pen. You think about the function return type that you specify at the start of a function definition, you might see that the type that is returned is actually a reference rather than a raw object. Where are we? Overloading operators. That's the other place you'll see them. And when we talk about overloading operators in chapter 18, we'll see sort of use cases of references. Now there are 3 types of references. 3 types. And this should hopefully look somewhat familiar. You have Lvalue references, right? That word Lvalue. It essentially refers to objects whose values we want to change. Okay, remember that Lvalue means we have typically with an Lvalue, it's an object with identity, where we have the name or have some kind of reference or address to that object. That's the Lvalue. So an Lvalue reference refers to references that refer to objects with values that we want to change. We can have const references, which refers to objects whose values we don't want to change, right? Again, that word const is apparent. And finally, we have Rvalue references. It refers to objects whose values we do not need to preserve after use. So for example, temporary objects. I think we talked about temporary objects in terms of like in the lifetime of object section in chapter 6. But Rvalue references, we're referring to objects that otherwise do not have identity. So we're not looking to preserve them afterwards. So we look at each of these types, especially Lvalue and Rvalue references, in more sort of detail. So 7.7.1, look at Lvalue references. So now we get some examples. In a type name, so when we're declaring an object, declaring a variable, the notation T ampersand means reference to an object of type t. And this is kind of somewhat similar to the pointer notation, where you had t star means pointer to object of type t, or address of object of type t. And this ampersand is just means reference essentially, not to be confused with the address of operator, which you would see on the right hand side of a declaration rather than on the left. Now, with one ampersand, t and then one ampersand, we use this for Lvalue references specifically. So I have a bit of an example. So imagine you have a function, void f. Void in this case meaning we don't return anything in this function. You might create some int v equals 1, and then you might have something like int ampersand r, and you initialize it using var. Right? Notice how if I didn't have this ampersand here, this code would also work, right? This code would also make sense. This is what I mean by the syntax for references and normal objects is kind of the same thing. But in this case, we're actually creating a reference. Like R is a reference that refers to the same integer as v. Right, so that R is a reference that refers to the same integer as v. And if I was to do int x equals r, right, x also becomes 1, right? Because r, again, we just treat it as if it's just the object. It's not. We don't think of it as an address. We don't think of it as we would with a pointer. It's just we just think of it as the value that it holds. So in this case, 1. So x equals 1. And if we do r equals 2, right? What happens? Both r and v have the value of 2. Right? Why do they both have that value? Remember, r is a reference to this. Oh, not bar. Sorry. R is a reference to the v variable. So in memory, if you got v over here and it's got a value of 1, r looks something like this. It actually refers to the same bit of memory. But references, this looks a lot like a pointer diagram, but references under the hood have sort of implicit dereferencing. Every time you mention r after declaration, like here and here, the dereferencing is kind of done for you without you having to do anything. That's the big advantage of references, is that you don't have to worry about handling the memory addresses to access the object. The access to the object is done for you under the hood. So x equals r actually means x equals the value that r points to for references. And r equals 2 means we're going to access the memory and then change this to 2. And that's why r and v both have a value of 2. In that way, I believe if you were to change v into 2, if this was to say v, I think the same thing would happen. I'll double check that though. I'll write a program to see what happens. But I know for sure, if you change the value of the reference, then this will point to it will dereference here, change it to 2, and both r and v will correspond to the value of 2. References have to be initialized immediately. As we said before, once a reference is made, it cannot change what it refers to. And the advantage of that is you always know that a reference refers to an object. A reference refers to an object. So references must be initialized immediately, because that sort of maintains this guarantee that a reference will always refer to an object. All operators apply. All operators and all operations are applied on the object that a reference refers to, right? I don't believe from memory. Yeah, no operator is applied on the reference itself. If you try, we talked about pointer arithmetic, where you can actually change the value of the pointer, change the address that the pointer stores using arithmetic operators. There is no equivalent for references. No operator is ever applied directly on the address that the reference holds. Any operator you apply, sort of implicitly, is actually applied to the object. Sorry, that the reference is referring to. And this is partially also why references can't change what they point to, because any operator will always be applied to its object. You cannot obtain the address of a reference. Again, because operators are never applied on the reference itself. So you cannot apply the ampersand operator on a reference to get the memory address of the reference. Because again, imagine I have this diagram. I've got my x integer, stores the value 2. I've got my r reference, which sort of is associated with the same integer as we had in that example just now. If I was to write ampersand r, or maybe let's have a pointer as well. Let's have a pointer p, which also points to this value. If I was to do ampersand p, what would be returned is the address here, right? Because pointers and references are also stored in memory, so they also have an address associated with them. So ampersand p would refer to this address here rather than the address here, because we can apply operators onto pointers directly. However, ampersand r, remember, all operators are applied on the object that the reference is referring to. So if we do ampersand r, implicitly we actually look at the object. We will never obtain this address here. We can't do that. That's what this point is. We cannot apply the ampersand operator to get the memory address of the reference. There is a memory address here, but we can't know what it is. If we do this, ampersand r, it will get the memory address of the two. Always. Right? Because operators are applied on the object that references refer to. And therefore, you cannot get a pointer of a reference. There's no, if we think of if we have int x equals 3, we can make int star p equals ampersand x. We can get a pointer to an integer. We can get a pointer to an integer. But imagine we first had int ampersand r equals x, right? Like before, we have some reference that we pointed to x, or that we refer to x with. If we then try something like int ampersand pointer p equals the address of r or something, that's not going to work. Primarily because this will actually give you the address of this, right? So getting the pointer to the actual address of r isn't going to work. Okay? You can only really point to the actual objects and not to references. You cannot get an array of references. And I feel like I remember looking at this. I don't remember why this is the case. But you cannot get an array of references. Trying to make an array of type, reference of integers or something, is not legal. And I guess as an analogy, you can think of references, kind of to summarize, references are a constant pointer, meaning a pointer where you can't change what it points to, that is always implicitly dereferenced, right? Every time it is used. So every time it's mentioned in code after the declaration, it is always dereferenced without you having to actually write the dereferencing operator. It's always dereferenced, so we always are talking about the object it refers to. And a reference cannot be, and no operators are applied on a reference directly. So we can never, a reference is not an object, and it cannot be manipulated the way pointers can be. Right? It's very easy to forget that references are not objects because we treat them as objects like this a lot because they are implicitly dereferenced. But they are not objects. That's important to remember. They're not the object that they refer to. And, okay, so a couple extra rules. An initializer of a non-const reference must be an Lvalue, right? We're talking about Lvalue references. initializer or non-const, I should say Lvalue reference must be an L value of the same type. Right, so we say int x equals 3. If we're going to make a reference R that is of type integer, then it needs to be and it's non-const, right? It has to equal an L value, right? Like x, a name for an object in memory has to equal an L value of the same type. Okay, trying to make this equal to 4. This is another way where references are not objects. You cannot make R equal 4 because 4 is not something in memory for R to refer to. 4 is a literal object. That's for non-const type. I've read non-const very specifically. However, if we're trying to initialize, so initializer, and what's on the right hand side here is what we call the initializer, just in case. Yeah. But the initializer of a const type can be an L value, like before, or it can actually be a literal of valid type. And by valid, we mean either the same type or a comparable type. So a type where implicit conversions are legal. So things like characters to integers, because characters are a smaller range than integers. So why is this the case? Why is it if we're going to use a constant reference, I should say constant reference, not const type? Why are we now allowed to use literals, right? Because before we weren't allowed to use literals. What happens under the hood is when you have a const reference, that is a reference that points to something that needs to be constant, immutable, the compiler understands that if you give it a literal, it can create essentially an implicit or temporary object that has no name associated with it and make the reference point to that object. So how do I want to do this? I might erase the first 2 points to give space and then I'll draw it out. So let's say we have some memory like this, and we have some code that says int x equals 3 and int ampersand r equals x. Right? Here we would have 3 with the x, and we would have the reference point to or refer to the 3. Right? No problems. If instead we were to do 4, right, try and give it a literal without putting the const, the issue is without the const, Lvalue references like this usually are used so you can change the value. Right? You're usually making an Lvalue reference to change the value that of the object that the reference refers to. But if you're giving it a literal 4, there's no way of being able to access that 4, right? Because there's no object. 4 is just a literal that you haven't written into memory yet. So what is R meant to refer to, right? However, if you were to do const int r, ampersand r equals 4 instead, right? The only difference from before and now is we've added this const keyword. Well, the compiler says, okay, I know that this 4 that the R refers to is never going to change because the const means whatever I refer to as the reference shouldn't be changing value. So the compiler is a bit more comfortable with this line and will do the following steps. It will do any type conversions if necessary. So for example, 4 is just an integer, that's not a problem. But imagine we did the letter A, character A. A is a character, different type, but using the ASCII conversion, we can implicitly cast that into an integer type. I'll just keep it as 4 for now. But any type conversions, so step 1, any implicit type conversions are done to make the 2 types, int and whatever is on this side, make them match. Then the value of the literal is placed in a temp bit of memory. Right, so we have some random bit of memory, and that 4 is written into that memory. And there's an address there. We will never work with it because it's temporary, but like we don't explicitly declare any variables or anything, but it's just some memory that is chosen. Just happen to do that, and then this temporary memory, this memory, is what R, this reference, the reference will refers to. So this R here now points to this. And it's much more comfortable, the compiler is much more comfortable with this because it knows that this value is never going to change. So it's happy to just use temporary memory to do this. And the temporary memory here persists so long as R persists. So while R is in scope, both this bit of memory and this bit of memory is sort of existing. Once R goes out of scope, for example, if you make R in a function and that function ends, so R is no longer in scope, that temporary memory is also going to be released. That resource is no longer going to be available to anyone. So yeah, that's the difference between these two. If you're going to make a non-const reference, it has to be, the initializer has to be an L value. Has to be something that you declared previously and given a value. I'll give it maybe you don't have to give it a value, but you don't have to declare it. But if it's an initializer of a constant type, constant reference, like this, then you can either use the L value, like before, or a literal of a valid type. One where you can one where it's the exact same type, or there's a potential method of casting into the type you want. Okay. There's a few more details about Lvalue references, but I think these, like, in terms of how they work and like how they are understood, I guess, by the compiler, that's the main parts. All right. 7.7.2, got Rvalue references. So R values are usually for referring to temporary objects. Right? We think of L values as having identity. R values, although it's possible they can have identity, normally we think of them as things that are things like literals or objects where we can't explicitly refer to them. So R values are for referring to temporary objects. Typically for modifying the object. So usually if we're going to use an Rvalue reference, we use it to modify or work with an object, and assuming it will not be used again. So knowing that a reference refers to a temporary object can turn an expensive copy operation into a cheap move operation. And there's a reference here to chapters 17.1 and 17.5.2, sort of explores this a bit more. But a couple of rules to bear in mind is an Rvalue reference can bind to an R value, but not an L value. Similarly, especially a non-const L value can bind to an L value, an L value reference, I should say. A non-const L value reference can bind to an L value, but not an R value. Right? So let's just go through some examples. Let's just go through some examples of where this kind of rule is important. How do this? Let's say we have a string. V, which is like hello. Right? And let's say we define some function, string f. So it's a function that does some stuff and returns a string, right? So it will spit back and produce a string value. Okay. So what would happen in terms of our cases if we tried to make a reference R1 to v, right? This is completely fine, because this is basically the same example we've seen before. We're creating a reference to an L value, an L value reference with 1 ampersand to the L value v. That's fine. However, what if we tried string ampersand r2, and then we call the function f? This is a problem. Why is it a problem? Well, the string that is returned by f, right? What this is going to do is going to call f, and then the string that gets returned by f is going to be this value here. The string is stored in temporary memory, right? It's not referred to by anything. It's not something where the name still exists. There's no name for it. So that string that f returns is actually an r value. So trying to give an L value reference and make it refer to an r value, that string that f returns, is problematic, right? So that's not going to work. Same thing if you try another like string literal, so like r3 by or something. Again, this is a problem because there is no name associated with this string by. By is a literal and therefore is an r value. So trying to make an L value reference refer to an r value is going to be problematic, and this is what we talked about before with non-const initialization. However, what if we try r value references? And the way we do r value references is we put 2 ampersands. So ampersand, ampersand. Instead of 1 ampersand, we do 2. So we have like r1. Now if we try this, this is okay. What's happening is the reference rr1 is being bound to the temporary memory that that string that f uses, that string that f creates and returns. It is stored into temporary memory, and that's what rr1 will bind to. Okay. Same thing with if you tried a string literal, so string ampersand ampersand rr2, and you tried by again. This is okay for the same reasons. By is an r value, right? It is stored in memory that you otherwise can't refer to. So binding the reference, the right value reference rr2 to that temporary, to that string literal, is okay. However, if we try to do string ampersand ampersand rr3 and assign it to the v value, remember v is an L value, right? V, this variable v, is an L value. It is a name that points to an object in memory. So this is a problem. This is not allowed. Binding an r value reference to an L value is not allowed. And of course, as we mentioned before, if it was a const L value reference, right, then that can bind to a literal. Yeah. So, and the other thing to mention, double ampersand is how we declare a right value reference. So 1 ampersand is for L value reference, 2 is for R value reference. And there's no such thing as a const R value reference. Right, we have const L value references, but there's no such thing as a const R value reference. In essence, because R values by nature are generally for referring to temporary memory, so having a constant for temporary memory isn't really doesn't really make sense. So no such thing as a const R value reference. Okay, move on. We usually use, so in terms of use, we usually use R value reference to implement a destructive read. This idea of a destructive read means we want to look at data, right? We want to look at the data that the R value reference refers to, but after we've read it and we've seen its value, we are happy for that data to kind of no longer be accessible in that sense of it being temporary. This allows for optimization for processes that would otherwise require copying. Right, from chapter 6, we talked about how copying is problematic because it's expensive, and there is an alternative operation, moving, which is a bit faster, which is a lot more fast. But the other thing to remember is that L values are immovable. You cannot move an L value, whereas R values are movable. That's fine. And then the other thing to mention is Rvalue references are accessed exactly the same as Lvalue references. And what I mean by that, well, we said with Lvalue references, if you want to get there, if you want to use them, you just type the name of the variable as if it was the object itself. Same thing with Rvalue references. And in that way, operators, getting the reference address, all the same rules that we apply to Lvalue references are also applied to Rvalue references. So it's the same idea of implicit dereferencing and things like that. All of that is kind of applied. All right, how do I want to do this? So to really show a really concrete use case of Rvalue references, it's good to remember that move operation and remember how it works and how it's faster than copying. So the example given, we want to create a swapping function. Okay. So the idea is you have void swap, and you take in a reference like A, take in a reference B, right, for objects of type T, some generic type, and we want to swap kind of what A refers to, what the value that A refers to and the value that B refers to. So, for example, you might have some memory like this, and some A which refers to it, and then B which refers to some other object, like that. And then maybe I'll draw it in red. So you got like a blue object and a red object. Originally, A corresponds to the blue object, and B corresponds to the red object. You want to make it so that after this function is run, B now refers to the blue object, and A now refers to the red object. Right? So it's the idea of a swap. Now, naively, what a lot of sort of beginners, and to be honest, I probably done this as well, like before I read this. What you would do is you would create a temporary object. So you would do something like T temp equals, or use the initialization, is initialized to A. And then you would do A equals B, and then you do B equals temp. Okay. Now let's look at what happens in this code. I'll draw it a little bit bigger. Just draw a bit more, have a bit more memory. So once again, you have the A reference, which points to a blue object. You have a B reference, which points to a red object. So the first thing that happens is this temp variable is created. And what happens in this initialization is there's actually a copy operation. Okay. Specifically, and remember, when I say copy A, I don't mean copy the reference. I mean copy the object that A refers to, because we never ever work with the reference directly. We always are working with the object that A refers to. So when I say copy A, I mean copy the reference. Sorry, copy the object that we're referring to. So we essentially copy this object, and temp refers directly to that object. So we've copied it. A equals B means we're going to do a copy operation again to make the A reference equal to the B equal to this object here. So what are we going to do exactly? We're going to take this memory and copy the values stored in the red object up to the blue object, essentially turning the blue object into the red object. So there's a copy operation that copies each of the values in the red memory up to the blue memory, turning the blue object essentially into the red object. So that's another copy. So we're copying copy B into A's memory. And B equals temp essentially means we're going to do the same thing, but we're going to copy the temp memory. So copy the values of temp into B's memory. So what's happening is temp, we're taking temp and we're going to copy the values stored in this memory down to this object here, essentially turning it into the blue object. Okay. And remember that these references would have been passed into swap from an external place, right? So these references still exist after the function is done. So we can access these objects via these references outside the function after the functionality is done. And we will see that the values across both have changed, right? Before it was blue object and red object, now it's red object and blue object. The only thing that will happen in terms of destroying any elements is this temp variable will no longer exist once the function is done because it's gone out of scope, right? Once we're outside this function, the function is terminated, this temp variable is out of scope, so it will go away, and we're just left with that. So in terms of functionality, it works. However, remember that copy operations are expensive, and we've done 3 of them just to do this swap. Okay, so that's where we have a problem, because imagine if you have a really long string like last time, 1,000, 100,000 character string, doing 3 copy operations is not ideal. Okay, so that's like the first method, the sort of naive method you might talk about. Now, the second method, we can label it as the static cast t ampersand x method. Okay, and you'll see why it's called that in a second. But same setup, right? You're taking in a reference that points to A. Now maybe make I'll make this blue again just for consistency. Taking in a reference A that points to this blue object, and then taking in another thing B that points to a red object. And you might say, okay, what can we do instead? Instead of 3 copy operations, what can we do? We begin by saying t of temp, very similar to before, but instead of initializing it immediately to A, we static cast with t ampersand of A. Okay, do I explain this in my notes what that means? Or kind of, okay. I'll explain what that means in a second. Well, I'll just finish off right here. Then we say A equals static cast t ampersand of B. And then we say B equals static cast t ampersand of temp. So, what does this mean? Okay. What do each of these static casts do? Remember that casting means we're going to change the type of the object, right? We're going to change the type. A was originally an Lvalue type. Okay. We have changed it into an Rvalue type. Still points to the same object, it still refers to the same object, but we're turning it into an Rvalue type. Okay. An Rvalue reference. Which means, what does that mean? Remember that Rvalue references point to Rvalue types. So, this blue object here, which was originally an Lvalue because it was referred to by an Lvalue reference, is now an Rvalue because it's pointed to by an Rvalue reference. We've casted A to become an Rvalue reference. And what that means is, before an Lvalue could not undergo the move operation. The blue object could not undergo the move operation. Now the Rvalue, which is the blue object, can undergo the move operation. And remember what the move operation entails. We kick out the old we kind of kick out the old label, the old reference in this case, so that it points to something that is unspecified, although it is still valid, right? So A still exists, but now it will refer to something completely random, like we'll just point over here somewhere. And temp is now the sort of label, the name that refers to this object here. Okay. Notice how we did no copying. There was no copy operation doing that. All we did was move what A refers to, right? Because when we turn A into when we do this initialization, essentially, we're doing the move operation. We're moving A out of the way and letting temp take ownership. Okay. Similarly, when we static cast t ampersand B, we're turning the red object into an Rvalue, and then when we do this equal thing, we're kicking out the ownership of B, right? B no longer owns the red object. And now with this A equals part, we're saying that A should be the one that owns the red object. And finally, I did say that the blue object was an Rvalue, but once we gave it the temp name, this blue object became an Lvalue. So once again, we have to cast temp now. We have to now cast temp into an Rvalue reference, so that the blue object can become can become an R value. So temp essentially gets kicked out. Still exists, but it no longer refers to that object, and we make b equal to that object that is referred to. So instead of just pointing to something random, b now points to the object, to the blue object. B now refers to the blue object. So before, we remember A referred to the blue object and B referred to the red object. Now, without any kind of copying, without actually moving elements around and making objects change their values, what we've done is we moved the ownership of which reference owns or refers to which object. So now A refers to the red object and B refers to the blue object. And again, once we finish this function and temp goes out of scope, we can still refer to these references, and they will now refer to the alternate object. So that's the idea of this static cast thing. We are turning an object into an R value by doing the static cast. We're turning the referred to object into an R value, which allows it to undergo this move operation of kicking out the old and bringing in the new, which is faster than copying, right? I think there was something I wanted to say, but I forgot what it was. Yeah. Something to bear in mind, when a compiler sees an initialization or a reassignment like this, where on the right-hand side it's an R value, right? Like in here, when we do this, we essentially make B an R value reference, meaning that what it points to is an R value. So when we do this, when the compiler sees that this is on the right-hand side, there is an R value, it will know to use the move operator if possible. What I mean by if possible, the T type that you use needs to have a defined move constructor. So for example, vectors, and I wrote an example code on this to really show how it works. Vectors has a move operator or constructor. Move constructor. A vector, which is a type, has a defined move constructor. So doing this with vectors, for example, will turn this vector into a right value reference. And so, because vectors have a move constructor, the compiler knows to use the move operation in this process. Some types, primarily the primitive types like int and things like that, do not have a move constructor because copying and versus moving an int isn't really going to improve anything because there's only one element, right? Copying is really more problematic if you've got like lots of elements that you've got to copy over. So that's what I mean by the type you have to have a type where the move constructor exists. So for that, in that case though, yeah, you get an R value out when you do the static cast, and then when you do the equal part, when you assign it to a value, you do that move operation, kicking out the old and bringing in the new. So that's the purpose of the static cast. It's to turn the reference into an R value reference, and therefore turning the object that it refers to into an R value, which can be moved. Okay, now, the only additional thing to talk about is the move function. And the move function, essentially, anytime we see static cast like this, static cast like this, we replace it with move. Right? There shouldn't be any white space there, I just wanted to make a point. Essentially, move and static cast do the same thing. Move under the hood is the static cast thing. So, in essence, when you see that word move, what you got to think is, whatever you put in here, first of all, you would expect it to be some kind of L value or L value reference. It's going to be cast into an R value reference such that the object being referred to, or the object in question, is an R value. And so that when we do, an initialization or assignment, the move operation actually happens. So the move operation, the move function, here, doesn't actually do the moving yet. It only does the casting part. But it's by casting it into an R value that allows the move operation to happen when you do A equals or B equals like this. So, in that sense, that's why we call it the move function, because it sets up the move operation by turning the variable here into an R value. So that's my understanding. That's my understanding of the move operator and the move function, and how R values references can be utilized, in this case, using the move function. And just to mention, all standard library classes can provide some kind of move constructor and move assignment. So this kind of thing. So this is for move construction, and this is move assignment. you can always expect, so like vectors, for example, are part of the standard library, so you expect them to have a move constructor. Same with basically any, like the string library, a string class, sorry, and other classes, the array library, they will have move constructors. Cool. Okay, so that's like probably the most tricky part. We're actually almost done. Okay, that's good. How are we going for time? Okay, so there's now just a few like more finer details about references in general. But we've explored the sort of types of references with Lvalue references, const Lvalue references, and Rvalue references. So the last sort of little chapter, the last little section of 7.7 here is just talking about the sort of when to prioritize pointers and when to prioritize references. So 7.7.4, pointers and references. Because again, we talked about this a bit, but they sort of have similar functionality and methods and reasons for use. But there are key moments, key contexts where you should use pointers, and key contexts when you should use references. So both refer to objects without copying, right? Typically by sort of working with the memory addresses instead. If you need to change which object you are referring to, use a pointer. Remember that once you use a reference and it refers to an object, it cannot change what it refers to. So if you want to be able to change what you're pointing at, you use a pointer. If you need to make sure that a name always refers to the same object, so if you want to always refer to, that's a weird refer, to the same object, naturally, we use a reference. If you want to use a user-defined operator, and again, this is part of operator overloading, which I'm not even very comfortable with, but at some point, if we ever learn what this is, bear in mind, if you want to use a user-defined overloaded operator on something that refers to an object, use a reference. And the reason for that is because you cannot redefine operators for pointers. Okay? So this idea of, I think it was mentioned before, when you want to apply operators on objects, it's easier to use references because references, when you use them, have the same syntax as the object itself. So you can just apply the operator as if you were working with the objects. With pointers, if you wanted to do that, you would have to kind of do some kind of dereferencing, and you can't even make user-defined operators. You can't redefine operators for pointers, because they have operators associated with them. Things like the arithmetic operators are already in use, and you can't redefine them. If you want a collection of something that refers to an object, use a pointer. Oh, I think I forgot to mention this. Okay. I'm not sure if I still talked about this. I don't remember. You cannot have an array of references. I might have to check why. I don't remember why that's not the thing. But you cannot have an array of references. Hopefully I'll have a reason on the screen because I don't know what the reason is. So it's doing something like int array 3 or something. Like trying to make a reference to I'm trying to make an array where each element is a reference to an integer, is not really something you can do. Maybe it's because if you try to do that, it will always just create a reference to the first element or something. I'll have a reason on the screen. But you cannot have an array of references. So if you want a collection, if you want a collection of objects that refer or point to another object, then use pointers. So yeah, if you want this idea of like having an array where each element is something that stores the memory address to other objects, then it is required that each of these objects in here are pointers, right, with values that are memory addresses, because references can't be stored in an array. And finally, the very last point is if you need a notion of no value, then pointers offer the null pointer. So there are moments where the null pointer, or the idea of null, is actually really suitable to a particular context. And if you find yourself in that situation, pointers are going to be more natural because there is no such thing as a null reference. There are only null pointers. So those are the kind of bits of criteria you can sort of use to try to figure out if you want a pointer or a reference. And with that, I think we are just about done with chapter 7.